Now, okay.
No, yes. Welcome.
So the camera caught us. Okay, so welcome to the second session, the afternoon session of the ROS Developers Day. I hope that you learned a lot during the conference this morning, and now you are ready to learn a lot more. Okay, so now before going any further, let me remind you to open the project of the next speaker. So the next speaker is Pablo Garrido, and he's going to start in a minute. But please start right now launching the project if you didn't do it before, because it's a big project and it's going to take a while. So you know how to do it because I explained in the morning, but we are going to put now a video that is summarizing the steps to do the launch of the project. Look for your event guide on your email. Then open the event guide. Browse down on the event guide until you reach the section which is entitled Speakers and Projects. Now, beside your speaker, the next speaker, you will see the project link. Click on the link. This will automatically copy the project of the next speaker into your ROS Development Studio area. Once you have your project here, click on the Open button and then again on the Open project. After a few seconds, your project will be open and ready to go. Now you are set up for the next speaker presentation.
Okay, so we hope you have the project ready. In this afternoon, we have 4 speakers, and also we are going to have the ROS Awards 2020 ceremony at 6:30 p.m. Don't forget, this event is very interesting. Stay tuned. And also, we are going to use a hashtag, right, for this event. The hashtag is ROSDevDay 2020. Please use it on social media. And here I saw some very interesting posts on our Twitter. Okay, so for example, this one saying all conference and no nap make Kai a sleepy boy. Exactly, we are not going to stop. We are keep pushing, we are keep learning this afternoon. And another example very interesting also is a participant is getting ready for the afternoon session with 2 screens here. And also the last one is my favorite. The robot is having lunch also in charging.
Charging, exactly. That's very
funny. Don't forget to use the hashtag on social media. And now let's go with our first speaker of afternoon section. So our first speaker is Pablo Garrido Sánchez, another software engineer at eProsima. Pablo is also an expert in DDS, but instead of applying it to ROS tool, he's going to apply DDS in micro and controllers.
Yes, exactly. So more concrete, he is going to show us how Micro-ROS works. So how to apply ROS to microcontrollers, and he's going to show us an example by using Zephyr. And here it is, Pablo. It has to be already ready. Are you there, Pablo? Okay, fine. Thank you. So if you are ready for your presentation, then the audience is yours. Go ahead.
Okay, so let me first share my screen.
Great.
Okay, here we are. Okay, so hello everybody, and thanks Ricardo for the introduction. I'm Pablo Garrido from eProsima, and I'm going to talk to you about Micro-ROS. During this talk, you are going to learn about what is Micro-ROS and which are its targets, how Micro-ROS can be used to integrate embedded system on ROS2 ecosystem, in which operative system does Micro-ROS runs. In this case, we are going to use the Zephyr RTOS. Later, we will talk about this. And finally, I'm going to show you some real hardware examples. Well, first of all, as I have said, I'm Pablo Garrido, and I'm a telecom engineer working in the Micro-ROS team here in eProsima. It's important to say that the Micro-ROS project is managed by the Opera Group, which is led by eProsima and also has Bosch, Fiverr, and PIAP as partners. So let's do a brief introduction about what is Micro-ROS. In short, Micro-ROS is ROS2 for microcontrollers. More specifically, Micro-ROS is a tool that allows ROS2 to be ported to different hardware targets. These targets are small microcontrollers and microprocessors which have a low memory and computing resources. Well, the Micro-ROS objective is that you can use ROS2 entities such as publishers, subscribers, or services on these embedded boards. You can find an in-depth explanation about all of this in this link to our ROS talk for Micro-ROS talk last year in the ROSCon. Well, the benefits of having a ROS2-like system in small microprocessors is that your ROS2 entities can directly interact with low-level hardware. For example, later I will show you a ROS2 publisher sending data directly from a sensor. You can also imagine a ROS2 node interfacing with some kind of sensor or actuator, such as screens or buttons or LEDs or whatever you can imagine in the hardware world. The main difference between other approaches, such as ROS serial and Micro-ROS, is that Micro-ROS aims to be a complete port of the ROS2 stack for microcontrollers. This allows porting ROS2 apps directly to Micro-ROS and enables a common API for having interoperability between different hardware boards. As I was saying, one of the Micro-ROS proposals is to keep the ROS2 layer architecture, that you can see here, as similar as possible. So we have a DDS-like middleware in charge of communication. We have an RMW layer. We have a ROS client library where the final user will code its application. And the layer stacks aims to be as similar as possible as ROS2. But Micro-ROS have some small difference with ROS2. The first of them is that we are not going to code in C++ or Python. Unfortunately, not all microcontrollers have a C++ toolchain. Some of them has, but not all. And Python is not so common in the embedded world. So Micro-ROS provides a C99 user API called RC-ALC. The second difference is that Micro-ROS not only use a network connection to talk to the ROS2 world. Thanks to its middleware, Micro-ROS is able to communicate with ROS2 nodes using transports such as serial ports or hardware buses like SPI or ETUC. The last difference is that Micro-ROS does not use a conventional DDS middleware. So let's talk a little about this Micro-ROS middleware. The default middleware used in Micro-ROS is the eProsima Micro XRC DDS. This middleware is not a complete implementation of the DDS standard, but is a wide protocol that can be used to interface with the ROS2 DDS world. You just need to know a couple of things. The Micro-ROS nodes need to talk with a Micro-ROS agent in order to represent themselves on the ROS2 world. As you can see in this graph, a Micro-ROS node will talk to the Micro-ROS agent using the XRC DDS protocol. For example, let's say that a Micro-ROS node wants to create a publisher. It will say to the agent, please create a ROS2 publisher for me on your site using the XRC DDS protocol. And then the agent will create these ROS2 DDS entities, and the Micro-ROS node can control them using the XRC DDS protocol. So just remember that a Micro-ROS node has to be connected to a Micro-ROS agent using a transport. And this transport can be UDP, TCP, or serial ports. And finally, let's talk a bit about where Micro-ROS can be used. The main targets of Micro-ROS are the mid-range microcontrollers. This device usually have around 200 kilobytes of RAM and about 1 megabyte of program memory or flash. They usually consume less than 500 milliamps and have hardware peripherals such as communication buses, general purpose inputs and outputs, GPIO, sensor or actuators. Nowadays, the Micro-ROS ports available targets the STM32 family, which have ARM cores of the M3, M4 series. So we have some reference boards. This red one in the center is the Olimex board with an STM32F407. This blue here is a similar one called ST Discovery that has some sensors on it integrated on board. And we also have a port of Micro-ROS for the Crazy Fly drone, which also features a STM32 microcontroller. As you can imagine, these microcontrollers can't run Linux. So Micro-ROS runs on top of a real-time operating system, an RTOS. We currently support 3 of them: Zephyr, FreeRTOS, and NATX. In this demo, we are going to use Zephyr because it provides a simulator where we can test our Micro-ROS app without hardware. Zephyr is a relatively new RTOS founded by the Linux Foundation, and it supports a lot of different hardware, and it has a really complete ecosystem to develop real-time application on microcontrollers. I even have seen ports to these RISC-V microcontrollers that are really common on FPGAs. On Micro-ROS, we don't support this yet, but it's possible to run Zephyr on that kind of systems. So let's start doing things. First of all, you have to know that Micro-ROS provides a build system. So let's create a workspace and let's install this build system. Okay. So first of all, we have to source our DASIN installation, DASIN setup bash. Now we are going to create a folder for this workspace. The Micro-ROS build system uses the same structure as a common ROS2 workspace. So here we have the folder created, and now we are going to download the build system. Okay, and we can build it using the common tool called. So meanwhile, that's done. Okay, so let's source our workspace installation. That's all. You have to know that this build system has 4 steps. The first step is the creation step, where you can select the desired hardware and RTOS. For example, let's run here ROS2 RAM Micro-ROS setup, create a firmware workspace.sh. And if we launch this step with any arguments, it tells us which are the available platforms here. So we can put here the RTOS name and the platform. The second step is the configure step, where you are going to select which Micro-ROS app are you going to build, and some other middleware configurations. Then you have a build step where the Micro-ROS app is cross-compiled to produce targeted specific binaries that in the flashing step you are going to flash on the board, the already compiled Micro-ROS program. So now we are going to see our first Micro-ROS application. Once we have the Micro-ROS build system installed here, I'm going to show you an use case demo. In this demo, we are going to see a Micro-ROS publisher and subscriber running in the Zephyr RTOS. The first part of this demo is going to be run on a Zephyr simulator. So we can see how it works and how useful it is in order to test our Micro-ROS apps. The first Micro-ROS apps will just publish and receive just integers. Then I'm going to show you the same code running on a ST Discovery board, the blue one that we have here. And this time the app will publish a sensor measurement and will modify the state of an LED when it receives the data from the subscription. So in order to clarify the architecture, let's analyze these 2 pictures. In the first, we can see the Micro-ROS apps running inside our Zephyr emulator that runs on or out on computer. Here, we are going to run this Zephyr emulator in the ROSDevDay. And this Zephyr emulator and the Micro-ROS application inside of it is going to use an UDP transport to talk with the Micro-ROS interface of the agent. The Micro-ROS agent has 2 interfaces, the Micro-ROS interface and the ROS2 interface. And in the ROS2 interface, it is going to talk the common DDS protocol to talk to ROS2 nodes. When we switch to the board, the Micro-ROS will be running inside of the microcontroller and will use a serial port to talk to the agent, and we will have the same topology, but with another transport. So let's start doing things. First of all, you have to know that creating the Zephyr workspace takes a little bit because it has to download all the cross compilation tool and all the Zephyr stuff. So I have prepared a ready to use workspace for you that is here in Micro-ROS simulation workspace. So you can imagine that we have already run this command, create a firmware for Zephyr and host. Host means this simulator. And now we are going to go through the configuration step. In the configuration step, if we run this command without any argument, it will tell us which are the available applications. So we are going to select this ROSDevDay app simulation. We also are going to tell the Micro-ROS client to use an UDP transport. The Micro-ROS node should talk with the agent using UDP. We are going to tell this Micro-ROS node that the agent is in the local host and that he has to use the port 8888. So if we run this command, we have our Zephyr application for Micro-ROS configured. So now we can run the Micro-ROS setup build firmware. Since it is already prepared, we can use this fast flag in order to have the build faster. That's all. Meanwhile, I'm going to show you how to open a Micro-ROS agent. I also have prepared for you a Micro-ROS agent workspace where you can run this agent because it takes also a little bit to download and build. But at the end of this document, you have the instructions to build your own Micro-ROS agent. So here we can go to the Micro-ROS agent workspace, and we have to source both our ROSDevDay installation, and we also have to source our local workspace installation. And now we are ready to run our Micro-ROS agent, which is in the Micro-ROS agent package and Micro-ROS agent application. We are going to tell this agent to use an UDP 4 version 4 IPv4 protocol in order to listen to the Micro-ROS clients, and that he has to listen on port 8888. Let's say that let's set the verbosity level to the maximum in order to see what is happening here. And now we have here our Micro-ROS agent. Well, before running the application, I would like to show you the code. Here in our Micro-ROS simulation workspace, we have created a firmware folder where we have all the cross compilation and Zephyr stuff. But here in the Zephyr apps and inside the app folder, we have all our Micro-ROS application, all the demo application that you can find using the build system. You can add, of course, more application to this folder. And here we have our ROSDevDay app simulation, which has some configuration files for Zephyr and for the build system itself. And we also have here our code. If we check this code, we are using the RC-LC API, which is the user client library for Micro-ROS. It's similar to the RC-LCPP, but written in C99. Here you can see how we are creating a Micro-ROS node, creating a Micro-ROS publisher of type in32. Of the same time, we are creating a Micro-ROS subscriber. We are also creating a timer that is going to be triggered every 2 seconds. And we also have a Micro-ROS executor on this layer. This executor has some real-time capabilities that are out of the scope of this talk, but they are really interesting, and you can find more information in our web page. So here we just add the timer to the executor and add the subscriber to the executor and just spin the executor. Okay, so if we go here, we can see that we have a couple of callbacks. The first of them is the timer callback that is going to be called every 2 seconds and will publish our data. And the data is going to be increased here. So we are going to see like 1, 2, 3, 4. And on the subscription callback, we are going to print which data is the Micro-ROS node residing. So let's run this Zephyr simulator. In order to run the simulator, we are going to use the same command as if we were flashing a board. If we run here our flash command, we have our Micro-ROS node running on top of the Zephyr RTOS, which the bill and so on. Here in the agent, thanks to the verbosity, you can see how this Micro-ROS node is talking XRC DDS using the UDP protocol in order to create DDS entities. He's creating a participant, a topic, a publisher here, another topic here, and data reader, and of course we should have also a subscriber. And now it is talking UDP in order to tell the agent to publish data on the DDS data space. So let's check if all of this works with our, if all of this works with our, I'm having troubles with the shells now. If everything works with our tools. So if we source of ROS2 dashing environment here, bash, okay. I don't know if the nodes are really running, but I'm going to test here ROS2 topic list. No, so I'm going to do it really quick another time. So let's open the Micro-ROS agent. Source of local workspace. And now ROS2 run Micro-ROS agent, Micro-ROS agent UDP4 with port 8888 and with a high level of verbosity. Is that okay? Okay. And now I'm going to run another instance of our Micro-ROS node on our Micro-ROS simulation workspace. Source opt ROS2 dashing setup bash, and of course source or local workspace here bash. And now ROS2 run Micro-ROS setup flash the flash firmware command. So I hope that now it works. And here we have our Micro-ROS publisher and our Micro-ROS subscriber. So for example, let's echo this Micro-ROS publisher topic, and we can see hopefully the same data that the simulator of the Zephyr RTOS is publishing. We also can, for example, publish some data on the other topic of the Micro-ROS subscriber topic using this type, this in32 type, and oops, sorry, let me that way. And we are going to publish, for example, data 1. Let's close. I think that is okay. Okay. So here we have how our Micro-ROS node is receiving the DDS data using the XRC protocol through the Micro-ROS agent. We can also increase the rate, for example, and we have more fast data. So this is the first part of the demo where we see the Zephyr emulator working on our local machine. But you can think that this is not so different from what you can do in your ROS2 application. So now I'm going to show you how easy it is to port this application to an embedded board. So here I have prepared for you a local environment. Let me put this webcam here. a local environment where we are going to build and flash a really similar application for this STM32 board. So first of all, let's see a couple of things of this board. We have here an STM32 microcontrollers, and here we have a TOF sensor. A TOF sensor is a sensor that measures distance using a laser. So we are going to see on the topic not just numbers, but the measure of my hand in front of the sensor. And using the subscription, we are going to turn on and off one LED that is placed here on the board. We have here two USB. The first of them is for programming the microcontroller, and the second one is the USB where the Micro-ROS node will mount an serial device and will be used to talk with the agent. So first of all, let me show you the procedure of flashing the Micro-ROS board. Here we have the same workspace as we have seen in the ROS yet, and I have run these commands. I have run a create firmware with Zephyr, and now not for host, now for the discovery IoT board. Then I have configured the ROSjet app, and now not using a UDP transport, but using a serial USB transport. Then I have built the firmware, and now we are going to flash it. So let's do it. And here we have the Zephyr RTOS being flashed on this board with the Micro-ROS node. If we see the code here, we can see that we have the same code. We are creating the same Micro-ROS node, the same Micro-ROS publisher, the same subscriber, the timer, the executor, and all the application looks like the one that you have seen. But in the callbacks, this time, I'm showing you the application of the simulation. Here you have the actual application of the board. It's pretty similar, but here in the callbacks, you have that now we are fetching a TOF sensor sample, and we are publishing this sample. And on the callback, we are using the data on the message, on the ROS2 message, in order to turn on and off the LED. If we receive a 0, the LED will be switched off. So we have here our board already flashed. Okay. So let me change the USB to the communication port. This is the communication port where the Micro-ROS node is going to talk XRCDDS with the agent. I'm changing the power supply of the board. And now here, I'm going to run a Micro-ROS agent. This Micro-ROS agent is the same agent that we have seen before, but it is going to use serial. And instead of providing him an UDP port, where we are providing it a serial port. So here we can run this agent, and here we can see how the communication is basically the same, but now the XRCDDS protocol use a serial port to tell the agent to use the DDS data space. And here I have prepared for you the same ROS2 topic echo command. So if we launch this, we can see that we are receiving the same the in32 data, but now this data is the data of the measurement of the sensor. So now we have like 50 millimeters, 60 millimeters. It depends on where I put my hand. Of course, we also can publish to this Micro-ROS node, and you have to check this LED here. If I publish one on the topic, on the subscription topic of the Micro-ROS node, this LED is going to be turned on because the Micro-ROS node is listening to this topic. And then if I send a 0, this LED is going to be turned off. And this is what I wanted to show you. Of course, this is a really simple, a really basic demonstration, because you also have here in the Micro-ROS environment ready to use services and actions. We are currently working on providing parameters And we are also actively working on the Foxy migration of this Micro-ROS environment. And finally, if I have some time, I would like to show you some other things here where you can find more information about this project. Here you have our Micro-ROS build system repository, where you can find how to use all that thing that I have been explaining, and you can ask for support if you want to add another platform or whatever. We also have this web page where you can find some tutorials and material about the design of Micro-ROS and all of this stuff. And finally, just in a couple of minutes, I want to show you some demos, some more complex demos that we have prepared in the project, and I think that they are interesting. Here we can see, here for example, how we are controlling a Kobuki demo which has an Olimex board on top of it running running Micro-ROS using UDP with the inertial unit, the inertial sensor of this drone in order to move. And we also have this drone, for example, flying here, and we can see its position in the common tool of the ROS2 ecosystem, that is RVs. This is one of our demos. In this demo, for example, we are using a TOF sensor, the same sensor that I have shown to you, to stop a Kobuki when it reaches some point in the space. You can see here where when the robot crosses the line, it does an emergency stop. This demo is also interesting. And here we have our last demo, where we have a robotic arm that uses a TOF sensor in order to measure the distance between the target and the bottom of the arm. So the arm can see where is the object, take it and move it to another position. Here we are also using an Olimex board with the Zephyr RTOS, and we are reading the sensor and publishing it to the ROS2 nodes that controls the robotic arm. Here in the corner you can see the RV's visualization of this demonstration, of this demo. So I think that for my part that's all, and if you have any question.
Okay, perfect. Pablo, thank you very much for your presentation. Thank you very much.
Thank you.
Okay, very good. And now, well, it's impressive, the demonstration, because you have shown first how to do it in software with the simulator, and then afterwards you have done it, you have shown actually the same things that you have taught, then how to do it with the real board, and we could, you could write and also read from topics in front of us. So amazing demonstration. And now let's go for the questions for you.
Okay.
Then please, guys, ROS developers who are there on the chat, then write your questions on the chat beside the video, and I will pass them through to Pablo. And in the meantime, let me ask him a question in the meantime that you are preparing your questions. So first one is that, so those demos that you mentioned, that you show at the end, that are the videos of the demos, also are quite interesting for applications. And what is the current status in terms of commercial applications that are using this Micro-ROS?
Well, we have been under a really active development last month. So, and we are now currently looking for a real application, a real demo of some partner or some company that wants to implement this XRCDDS protocol. But for example, I think that I have heard that some other mates of me in eProsima have worked with a PX4 drone, which features this XRCDDS protocol in order to communicate the drone, the actual hardware and the firmware of the drone, which is in the Natex RTOS, in order to communicate these parameters of the drone to the ROS2 data space. So I think that is a really interesting application.
Okay, makes sense. So drones, I think it's a very good application for for this kind of technology, right? Because as it was Rafael who was mentioning on a previous session that the power consumption in drone is something very it's a limiting factor, and then by putting microcontrollers there, the power consumption can also be decreased, and then if you have Micro-ROS inside it, then you have a drone which is running ROS directly.
For example, let me say that in this board, I don't know if I have mentioned it, but this specific STM32 is a low consumption device, which has low consumption modes where you can put the microcontroller to sleep, and maybe it's consuming like microamps. So I think that for Micro-ROS application, it's really interesting to have ports to that kind of devices.
Great. Okay, let me see if there are some questions here. So I have one here from Bytegrity that says, what are the requirements for an RTOS to use Micro-ROS? POSIX-like interfaces only?
We have this is a really interesting question. In order to run our middleware, we have just some timing function required. And we don't need any POSIX compliance to run XRC-DDS. But the higher layers of ROS2 needs POSIX compliance. So, for example, NATEX provides POSIX compliance. Zephyr, of course, provides POSIX compliance, and FreeRTOS has add-ons that can be integrated in your project in order to provide these POSIX functions in order to build the Micro-ROS environment.
Okay. And then another question here from Siam Ganatra. How much minimum RAM is necessary to run Micro-ROS?
Okay, I have to say here the same that before. In order to run the middleware, the XRC-DDS middleware from eProsima, we only use like 30 kilobytes, I remember. And all this memory is static. When you add the Micro-ROS layers on top of the middleware, you have some dynamic memory. For example, our RMW is written with almost a static memory, but the RCL layer uses dynamic memory. You need about 120 kilobytes of RAM in order to run it properly. But maybe if you have more, it's okay, because when you are writing an application, you will need to use more than one topic, more than one service. So maybe let's say 200 kilobytes.
Okay. Fair enough. Okay, great answer. Then I have here another question. Let's make this the last one. And also Jaime Martin Loza, who is the CEO of the company of eProsima, is also on the chat and is answering some of the questions already. So he's helping us with that. So let's go with this one, the final for Pablo, from Frank Loesche. He says, does it work, Micro-ROS, on all boards supported by Zephyr, NewtX, and FreeRTOS, or does Micro-ROS add additional constraints? So you require something in order to be able to be running any board?
I think that the only constraint that you have in order to run Micro-ROS is that you have enough flash, which is not so difficult to have enough flash in a board to run Micro-ROS, because boards usually have a lot, and you have to have enough RAM memory. But I have not tested it, but maybe you can port or build system to another Zephyr board. Yeah.
Okay.
So I think that is not so difficult.
Okay. Very good. So thank you very much, Pablo. Thanks a lot. Thank you for your presentation, and see you around the world. Okay.
Okay.
Thank you, Pablo.
Bye.
Okay, for continuing, please, ROS developer, remember to open the next ROS chat of our next speaker, Andrei Kholodnyi. You can find the project in your conference guide. Please get ready with this project to be able to practice with the next speaker. So as with this morning, we are going to have some fun while the next speaker is getting ready. So now we are going to have a prize quiz again, and we are going to play a very short video, a very specific topic on ROS. And in the ending of this video, you are going to see a question related to this video. And the first one who answer the question correctly in the chat will get a t-shirt, an ROS developer t-shirt sponsored by eProsima, and a coffee mug sponsored by Robotics company. So let's see the video.
Wait a second, but do you have to answer the question after the question has been posted? Okay, please don't try to guess the answer like you were doing before. Okay, let's go with the video.
Welcome back, ROS developers. This question is difficult to decide the winner.
To get a winner for that one. Oof, yeah. So because more or less all the answers, but really not one is clear enough. You know, so. Then finally, what we are going to give as the final correct answer is the one from Mikel Larrea, interface the simulation and ROS. So actually by robot is more than that, but in the context of the video is the environment that allows us to interface this habitat sim with ROS. So you can publish and get data from the simulator. So Michael Larrea is going to be the winner for this one.
Okay, congratulations.
Yeah.
So now let's continue. I hope you have the roadmap ready for this presentation. So the next speaker is Andrei Kholodnyi, the principal technologist at the CTO office of Wind River Company.
Yeah, exactly. So Andrei is going to teach us how we can cross-compile ROS2. That means to compile the whole ROS2 system to generate code for another platform, which is not a Linux PC, a typical Linux PC where we are running usually ROS2 or Windows PC also. Then he's going to show us how to cross-compile specifically ROS2 for VxWorks operating system using an ARM processor. So let's go with Andrei. And Andrei, are you there? Can you hear me?
Yes, I can hear you.
Okay.
Can you hear me?
Yes, great.
Excellent.
Yes. So if you are ready, Andrei, then the audience is all yours.
Thank you so much. So I can start, right? So hello, everyone.
Yes.
Unfortunately, I cannot see you. I hope you see me, right? So and I probably switched right to the now to the presentation mode. So welcome to this talk, and this talk would be about how to cross-compile ROS2 distribution by taking VxWorks real-time operating system as an example. And I will just go through and explain why we need it and so on. But first, let's say, let me introduce myself. Who am I? So this is me. I hope you see my screen, right? So.
Sorry, we are not seeing your screen, Andrei.
Do you see my screen?
No.
No, you don't see my screen.
Not
but
now.
I have shared it.
Okay, can you?
Wait a second. Wait a second.
Yeah.
Well, actually, I should share it. Wait. Do you see my screen now?
Oh yes, now we can see.
Oh, sorry. I apologize for that.
No problem.
So, sorry.
No problem.
Yeah,
that's normal.
So, yeah, it's like, you know, it's like always like a problem with when you do remote something, right? So
yeah,
now you see my screen, right?
Yes,
okay, so
correct.
This is yeah. Thank you very much for joining. So this is my topic for today, right? So I will go through the how to cross-compile ROS2 distribution by taking VxWorks ROS real-time operating system as an example. Actually, I think previous speakers will talk or spoken about different operating systems. I know that the eProsima guys probably spoke about Zephyr or there is also FreeRTOS and other operating systems which ROS2 can run upon. Is not only Linux but the let's say the approach how to do the cross compilation is more or less the same, right? So and I will go and explain you why we would need to cross compile and in particular how I will talk a bit about principles how to, let's say, tune ROS2 distribution that you can, you know, shrink it a little bit and to understand what paths can run where, right? So, but before we go to this topic, I will tell about myself. So my name is Andrei Kholodnyi, and I'm a principal technologist, as it was mentioned in the technology office. And I have this, this is a part of technology office, this privilege in the company to do like stuff which I think it's interesting and good for the company. So my topics of interest is mobile robotics, in particular ROS2. So I am a real-time, I am core chair and real-time working group in ROS2 community. And I'm also looking in, because we have a VxWorks, it's a real-time operating system. I'm looking in particular in TSN and in the computation on the edge, because with TSN you can create pretty cool then distributed real-time operating system, right? So then why WindRiver? I don't know whether you guys know WindRiver. Probably I would know if I would stay in the auditorium. I would say, hey, please raise your hands who knows WindRiver, right? And probably this is NASA. This is the most famous example. So we produce a real-time operating system, which is called VxWorks, and since many years, for instance, all Mars rovers which are running on the Mars run with our operating system. And besides that, we have a bunch of all robots, industrial robots, which are mentioned here from KUKA, ABB, Schneider, Yaskawa, General Electric, Siemens. They come out, they run our operating system. So inside, that's why it's some kind of natural why we have interest in ROS2. So what is done in ROS2? So just few words about VxWorks, right? So what is VxWorks? VxWorks is a proprietary real-time operating system. It is a POSIX compliant, and that's why it's quite I think quite easy. I would say to port POSIX user space applications on VxWorks. So it has kernel and user space separation, and it has also C++ support. Then it has a LLVM toolchain, and we have, in compared to open source, we don't have open source C++ libraries, but we have a proprietary also Dinkomware C++ library, which comes from Dinkomware. And we have also like a normal Eclipse-based or VS Code IDE where you can develop VxWorks whether on the Linux or Windows hosts for different targets. And the first bullet, so we do support basically ARM, Intel, MIPS, PowerPC, RISC-V. So it's pretty broad range of the architectures which we support, and this is mostly embedded, so embedded targets, right? So let us move further. So let's say what is because I mean in my talk I will talk about cross compilation. I would, before we move, right? So I will try to explain the terms which I use in my presentation, right? So it's cross compilation. Then what is native compilation, right? So what is this? So by definition, the native compilation, when you compile something on the platform A, and then it produces some artifacts like binaries, libraries, and whatever. So it produces these artifacts for exactly the same platform. That's why it's called native compilation, right? So in this particular example, I put just two systems, right? So you can, for instance, what normally done, right? So you have your Ubuntu machine, it's probably Intel machine. This is shown on the left side, and then you are able to compile everything. So you have your tool chain, compiler, linker, and so on. So then you have a different tools for the to compile ROS2 itself. So it's CMake and after tools, and then special tools like amend, calcon, and so on. And then you compile this, and then you run everything on the target. Let's say you can run applications. In this case, it's, let's say, hello world. You can do the same basically on any other on any other hardware. If you would have the same environment, right? So if you would have a tool chain and the compiler and so on, so you can do the same on Raspberry Pi, for instance, right? So and this is called then cross compilation. Sorry, native compilation. What is then cross compilation? So cross compilation, let's say, if you would compile on the one platform binaries and artifacts which are dedicated for another platform. You compile on the platform A, binaries for the platform B. So it could be that you have you compile binaries for platform B, and platform B is Linux, but you can also compile this for any other operating system, not necessarily Linux. And I will show you how to do this for VxWorks. And by looking into this, I think it's pretty easy then to do the same stuff. It's some kind of basic principles to do the same stuff for other operating systems, not only VxWorks, but for QNX, let's say, or for eSol, for FreeRTOS, and so on. So why we need to cross-compile? Just a few words, right? So it could be that, as I have mentioned already, you need to compile for the different operating system, and this operating system don't have a native tool chain. So there is no compiler which allows you to natively, for instance, compile ROS2 stack, right? So, and that's why there are many operating systems which provides only cross-compilation tools, and these cross-compilation tools you need to take to be able to cross-compile for another operating system. Then, for instance, you might have even you have native compilation tools, but you want to run binaries which you compile on another target, right? It could be not only Intel. Intel is very generic, desktop PC, but it could be like ARM or RISC-V or other hardware, and it could be so tiny hardware which you want to run ROS2 that you don't even want to install a complete development environment, and you don't, if it is embedded, for instance, hardware, you might not even have, let's say, HDMI, so display. That's why it's pretty inconvenient and slow sometimes to build natively. That's why even you would have a possibility to do so, you would then go and cross-compile for the your target operating system. And then if you want to run something on this target, you might want to, for instance, tune your target system for performance and for the footprint. And if you would like put a full-blown development environment on your target system, then it would be pretty difficult then to squeeze all this stuff to make it, you know, compact and remove all components which you don't need. And for that, like, cross compilation is a good option, right? So then let's say how to cross compile, right? So what you need for that? First of all, you need a cross compilation tool chain. So you need apparently the source code which you want to compile. Then you need a cross compile tool chain, And tool chain is called tool chain because you need, let's say, chained tools which allows you to produce at the end artifacts, right? So it might be like a compiler, link, archiver, and you just pass your source code through those to get at the end the binaries, or it might be any other tools which produce configuration files, whatever. So that's why it's called the tool chain, and you need a cross-compile tool chain, right? So it's pretty easy, for instance, to install it, to get it for ARM, for Ubuntu. You just go and do like sudo apt install, and you install this ARM toolchain, which I have mentioned here. What you might also need, except this and the source code, you might need also to install QEMU. So QEMU is the emulator, and this emulator, you just install emulator which emulates your hardware and your target hardware, and then it's not necessarily, so the beauty of this approach that you don't necessarily even need at particular stage your target hardware. You can build like everything, and you can run everything on your development PC. So for that you don't need to have your hardware target at the beginning, or you can have those in parallel. So where to get these cross-compiler tools? Well, for Linux, it's clear. You just I have mentioned Ubuntu. Then, if you want to go to other vendors, then depending on software, on the operating system and hardware support, you might go directly to vendors and get tool chains. So if you want to try VxWorks, I have put a link, so it's freely available. You just go and install software development kit for VxWorks, and then there is a tool chain inside and precompiled binaries, as I said. So we are, as one of the vendors of other operating systems than Linux, provide tools for that, right? So, and I will take this as an example, and go through this, and then oh, wait a second.
Hey, Andrei, I think that is missing something in there.
Yeah, I think it's missing something. Oh. I think it's...
Maybe you, yeah, can you open the, again, go to the main ROS here. Okay, go ahead.
Yeah, let me go. So back.
Yeah, so go to the RDS.
Yeah, just go to RDS and then
RDS, yes, Jupyter Notebook, exactly. Let's go there.
Do you see something different on your machine?
Yeah, well, I'm telling you now. I don't have this open, but I remember that it's missing the part of the compilation with the Hello World example. Yes, all that, and then all
but I have just
maybe you open the ROSjet that is not the correct one, the last one version that you did. Can you go to the world icon that you have on the top menu, top menu, top world icon? Yeah, there on the right, top on the right. There is a, yeah, is a ball. No, not that one. A ball. Yeah, the wall, exactly. So let's have a look here. I think that you are opening another one. So it's not there. Okay.
But I have just opened that, and it was, everything was there. You know,
okay.
That's why I'm just
wondering. No problem. Let's do one quick fix. So let me send you.
Wait a second.
Let me send you the link, the proper link here, and put it on the chat here. So no problem, no problem. We are almost there. So can you go to the chat and then?
No, it's fine.
Yeah,
it's fine.
go there.
Yeah, let me. Yeah.
And then now you have the proper copy where it says final. You see that it says final?
Is it on the right side
On the left,
or on the left side?
Yeah, that one. Yeah, on the left. And the name of the ROS yet
on the left.
Yeah.
This one. Final.
Okay.
Exactly.
That's the one. Can you open that one and then in theory, this is the one that should contain everything.
All right. So let us wait. But I think I think I have opened everything and let's say checked this before and everything was there. That's why I'm just wondering, what could be wrong here.
I don't know. Okay, opening this is going to be a bit strange because it contains all the code for the cells and so on.
No, it's fine.
Okay.
It's fine. Yeah. Apparently, it's the same. Apparently, it's the same. I don't know why it happened.
Okay, so let's go on that one. Yeah. And we'll have to wait until this one is open.
Yeah, we just need to wait a bit.
But that doesn't make any sense right
now.
It should open very fast. It should open very fast, and it should have closed the previous web shell. It should automatically. Yeah. I don't know.
Yeah, but this is how it works. I don't know why it. Yeah.
Okay.
I think we need to wait.
It's going to take a little while.
A couple of minutes, right? I really apologize for that, guys. Just because I have checked that before the start and everything was there.
And can you close that one because this one doesn't make any sense? This.
Yeah. I will close then this
one,
right? So not this one, but this one probably, right? So I will close this one.
Yeah, okay,
and
that
this
one is
one
correct.
Also I will close, right?
No, not that one. Exactly, that's a good one. Yeah, right.
No, I'm waiting here.
Yes,
I'm just
correct.
waiting here.
Okay, so maybe.
Yeah, it's just there, I think it's nothing. Yeah.
So maybe
nothing
in
serious.
The meantime, I can ask you
a bit.
One question. In the meantime, maybe.
Yeah, sure.
So for example, you are showing us how to cross-compile ROS2. Okay, but ROS2 has a lot of packages in it, and could it be that some of the ROS2 packages cannot be cross-compiled for a given target platform? Could that happen?
Yes. So actually, you are right. Some packages cannot be, or let's say it's pretty difficult to cross-compile them, just because they have for instance, they have some libraries or some, let's say, some functions which are missing in the operating system you want to compile.
Correct.
For.
Exactly.
For VxWorks, is there like a good example of that is fork and exec. We don't have fork and exec, and if, for instance, any package has fork and exec, we cannot compile it, right? So
got it. Then here we have this new version. Then let's go to the bottom and then let's see if you have all the information. Yeah, there it is, right?
Yeah, right. So this is the right one.
Please go.
I was really wondering why.
No, don't worry. Don't worry. It's normal. This is a live
demo.
Why this is a live demo, so this kind of things happen. So don't worry. As you can see, we can solve it. Let's go.
No. I'm just really apologize.
No need to apologize. No need. Go
ahead. Good. So as I said, how to cross-compile, I will take SDK as an example and to show you how to cross-compile everything. But let us start with native compilation, right? So what I have prepared to you is a small example, right? So which you can please open this example, right? So and you need just to go to let me check where I am. I will open now my shell. So and if you go to this shell and you will go to the notebook, right? So if you go to the notebook workspace and then you go to examples and you do cat, let's say, hello world, you would see this simple example. So this simple example will help us to identify. It's like a hello world, but for the operating system, right? So this simple example will help us to identify what operating system we are running. For instance, it will be a Linux or whatever, and then what machine. So it's very simple. It just it does hello and then print a sysname and print a machine. Before we run it, so we will use a GCC, right? So for that, and let us look where GCC is located, right? So if you do, for instance, like which GCC, right? So you will see that GCC is located in the root folder, and normally, so you should be able. It depends on the compiler which you are using, right? So, but if you are using GCC, for instance, you might do like print multi-arc, and it will tell you for what operating system it produces binaries, right? So in this particular case, it produces the binaries for Intel, it's x86-64, and it will produce binaries for Linux, right? So then let us then go and try to compile it. There are other versions of this called the triplet. Basically, it tells you what hardware, what operating system, and then it's GNU or other distro. So you can go to this link if you want and look what kind of other tool chains exist, right? So you can go and see what is the convention for that, right? So but now we will go and just cross compile it. It's just pretty simple. So it has cross-compiled, and we will see that there is a hello binary. So now we will then go and try to run this binary, right? So we run this binary and see what happens now. So we run hello. And we will see that it prints hello Linux. So Linux is the operating system, and it prints target machine which this binary runs on. It's x86, and this is the native compilation, right? So it has produced the binary for exactly for the same platform where I have compiled it. Now, if you might also look at so there is a file cat in Linux. So you might go and also look what kind of binary it is, right? So it looks in the ELF header of this binary and prints it for you. So it says the same, right? So it's a ELF binary is 64 bits for the same architecture and for the so this is a native compilation. Then we would go and try to cross compile it. So first of all, so it will be absolutely the same, right? So the let's say, the same procedure, and we will take the same source code for that. But what we need to do, we need to go into I have installed a cross-compilation environment, and then we need to go and to initialize this compilation environment. So we just go and initialize this compilation environment, right? So and now let us see what we have done, right? So let us see what we have done. For instance, if we go and implement variables, right? So and grab for WinDriver. If we go and grab for WinDriver, we will see a bunch of extra variables which this script has set it up, and I will go then and show you let's say most important variables, right? So it for instance set a compiler. It will be a different compiler, not GNU compiler, but WinDriver C compiler. Then it sets some compilation path where this compiler is located. It sets a sysroot path, and also it adds this path for the compiler to the path variable. That if you go and do like which WinDriver CC, so WinDriver CC, then it will show you that it is located under SDK directory in this case, and this is how it will work basically for all cross compilation environments. So if you would install them, you normally install them not in the root folder, but in some separate folder, and then you need to pass some settings to be able to use it, right? So this is I have shown you. So if you do like as I said, if you do which on the compiler, it will show you where it is located. Then let us probably do the same. It's a little bit different for the WinDriver cross compiler, right? So it's not like print multi-arc, but target triple, and it prints x86-64. So it also prints operating system. I will show you in a moment why it doesn't do that. But at least we see that it will produce also binaries for x86-64. So and then let us then go. So why it didn't shown us OS type, right? So where let's say GNU CC compiler showed that, right? So basically there are in ELF format also there is a ABI, OS ABI defined for the various operating systems, and just few OS ABIs are defined there. So basically, what is supported is FreeBSD, Linux, of course, Sun Solaris, and VxWorks in particular doesn't support that, as well as other operating systems, just not described there. So basically, if you would compile binaries for other operating systems, like for FreeRTOS and or for Zephyr, it will show you probably the same, like it will show you that it will compile for the hardware architecture, but it will not show you then the operating system, right? So then let us do and let us go and build the same stuff, right? So we have compiled it with our compiler, with cross compiler. And now what happens if you would try now to run it here on the target, right? So remember I said that this is a cross-compiled binary. Let's say whether it will run. Well, it does not run. So apparently because even it is compiled for the same architecture and it tries to execute, it was compiled for the different operating system, and it has a like a different OS ABI, so that's why it's not possible to run this the same like hardware architecture binary on Linux operating system. Now, if we will go and look what it prints now, right? Instead of so in compared to the native compilation example, it will show you that it is the same like 64-bit executable, but instead of Linux, it's just show you that it's compiled for sysv. So this is exactly the reason I have explained you that file just looked in the ELF binary format, and there is no VxWorks support for this ELF format. So you would see probably, like in our case, is some kind of neutral. It is actually 0, right? So not non-defined. You will see that if you would compile binaries for other operating systems. But this kind of combination on the development host will help you to understand, for instance, for what architecture and what operating system your binaries are compiled. Because sometimes you compile something and you're not sure for what it is compiled, right? So and by these simple commands, you can just go and look and see what it has produced, right? So now let's say how we can identify that it is compiled for VxWorks. Well, it's pretty difficult, right? So, and I talked to our OS guys, and they say, for instance, the only possibility is to go and grab for some kind of specific symbols, right? I don't think it's very like operating system specific. You can go then and grab, and then you see that it's by that means you can see that it is compiled for different operating system, and you might see that it is compiled for VxWorks, but not for, let's say, Zephyr, or not for QNX, but it is some kind of, tribal knowledge, which quite difficult. You need probably to know. You need to go and ask how to do this, right? So then where can we run it, right? So one possibility would be to run it on the target, on the real target, but luckily us, we have this QEMU, right? And then I will show you how to run it on the QEMU. So for that, I have prepared quite a long line with QEMU parameters. But before I go to that, I will explain you how it works. Basically, so QEMU is a binary which runs on the Linux operating system. But what this binary does, it just emulates different hardware, right? So in my particular case, it would emulate the same Intel 8664 hardware, but it will also emulate, or it can emulate ARM or PowerPC or other hardware like RISC-V. And then on top, I would run, you have seen that VxWorks binaries does not run on Linux. So you need a VxWorks kernel. And then on the top, on the top of this kernel, I would run hello world, right? So, and you just need to go and copy this long command and paste it here. So what this long command does, it just picks up. So in the SDK, it is prepared VxWorks as a kernel. So you would see then this VxWorks would boot. And then what it will do, it will map current directory. It will map as a USB storage device that we can then pretty easily map this current directory as a FAT32 file system into VxWorks, and then can run command out of it, right? So and this would be pretty similar. Probably then instead of VxWorks kernel, you would run any other kernel, like you can run in this particular case, You can run also Linux kernel, or you can run FreeRTOS kernel, or you can run QNX or whatever. So it's pretty then flexible way to emulate your target hardware on your development host, right? So we run this. It takes a little bit time until it will start. So now you would see that VxWorks has started, right? So it's a VxWorks, you see VxWorks logo and saying it was compiled. You can see also that it is like a x86 and so on. So now we would just go and because it is mapped, so we will go and execute our binary. So for that, just go run. So we switch to the command interpreter, like we do like cmd. And this is like more or less similar to bash, what you can do with that. So then I would say I will show then, or I will see what kind of, I need to find my USB device mounted, and this is actually USB device which is mounted. So I need to go to this USB device. So BDA 0A. So and then you remember it was like it was a current directory was mounted. So I can do, for instance, hello.c and see, okay, this is the same file, and then I would run it, right? So and this file was crashing with a core dump on the Linux target, but using then QEMU, I can easily run it, and it will show that it runs on VxWorks, and it shows that it runs on this long machine name. Yeah, it's x86 processor with some SMP support. So you then just go, you do like this Control C, for instance, and yeah, you can do, I hope, yeah, you can do Control C, and this is it. So this example is terminated, and we just go and look. What do we need to do to cross-compile ROS2, right? So what we need to do, I picked up Dashin sources for that. So and these Dashin sources are located here, right? So we need the same SDK. We need so it's exactly the same compilation toolchain, the kernel, and the only extra thing we need toolchain CMake and platform CMake. Because ROS release is source code is a CMake based, right? So and then I will apply some patches which you probably don't really not interested in. It's just VxWorks specific patches. But what I would like to mention, for instance, that probably if you would compile ROS2 for other operating systems than Linux, you might need to patch it, right? So so we provide the patches for ROS2. So I hope that other operating system vendors or community, in case of FreeRTOS or Zephyr, could provide patches for that as well.
Andrei, 5 minutes to finish.
Oh, all right. So then, what I would show you that I would like to mention a little bit about toolchain CMake and VxWorks CMake, right? So you need them just because you need to define a different operating system. So all these parameters and different paths to your SDK and so on to be able to show CMake where to pick up proper parameters, right? So then the other important stuff which I want to explain you is how to strip down ROS2 build so that you don't need to build all packages. And as I have mentioned, for instance, I will show you here. I actually need, or in many cases, you don't need tools, or you don't need visualization binaries which you can still run on your development PC, but you need just a small subset of the binaries which you would run on your target, right? So, and this how it works on ROS2. So you can like whether you can ignore directories, right? So which you say, okay, I don't need them. For instance, I have ignored here Python if I don't need to install Python, and I have ignored all visualization stuff because I don't need them on the target, right? And I say in this particular case, because I want to show a very small example, I say I want to build only these packages, right? So up to these packages. I don't want to build everything. So then let us go to this directory. You will see it's a normal directory for ROS. How you know this? And the only difference between cross compilation, let's say if I want to native compile, I would use probably this kind of structure or this kind of command for the native compilation. If I want to cross compile, what I only need to do, I just added another path to the toolchain file where it is located like in my SDK, right? And also I have added some prefix paths just because I want to show that I have compiled dependencies, so ROS2 dependencies for VxWorks, and they are located there, right? So, but if I would copy and run this command, so I would run this command. It's pretty similar to what we have shown before. It starts compiling this example, right? So it's very similar, and it takes like 5 seconds to compile, and it has actually cross-compiled that, right? So it's pretty easy. You just prepare, and then you do the same stuff. And then, all right, so the last probably stuff, how you run then this example, right? So I have basically copied all binaries which I want to run here under this directory. So it is located on the export root. And if I would go, we can see all these binaries, which I have cross-compiled. And yeah, so let us run these binaries. And we do the same because it's for VxWorks. We just start exactly the same QEMU command, but I would say instead of just current directory, I just map as a USB this root directory. So I just run it. We wait a bit. So it is the same VxWorks prompt. I will go to the interpreter, and then I would then set up some variables just because it is not on the root, but under under the other non-root directory. So I just do this, and then I just jump to the binary directory, which I have shown you. So you can look and see that all these binaries are here, which I have cross-compiled, and then I would just run. I would just run this simple, yeah, in this case, like time lambda example, it takes a little bit time just because it's, it's emulated. It does not run on natively on Linux. But at the end, you will see the same hello world coming out. And this shows actually how to cross-compile and how to run your ROS2 binaries on other operating system and on other target architecture. You can still use your development host for this, and I think it's just really great. And I come to the conclusion. So what we have seen yesterday is, so today we have seen how easy to cross-compile ROS2 for non-Linux POSIX OS, VxWorks in this case. We have learned what are the differences between native and cross-compilation, and this is actually applicable for any cross-compilation, not only Linux, but also non-Linux platform. We have prepared and set it up cross-development environment. We know that we need a cross-development environment, and we built ROS2 binaries. So ROS2 binaries can be built absolutely the same way for different operating system with small differences as you do this for Linux. Then I have briefly explained you how to split ROS2 packages. So you don't really need host tools, and you don't really need the visualization tools on your target system. You can, by applying call ignore and by selecting what kind of packages you want to build, you can just squeeze your ROS2 distribution to cross-compile only the packages you need. And then we have seen how to use QEMU to run these cross-compiled binaries on the development host. And this is really convenient because sometimes you don't have even hardware yet, but you can still already run and try it out how it works on other operating system or on other architecture. So this is my last, let's say, last sentence. Thank you very much. Do you have any questions?
Okay, thank you very much, Andrei. Thank you. So now it's time for questions for Andrei. Great. Can you, please, Andrei, can you switch to the camera so we can see you in the meantime?
Yes, wait a second. I just go here. I just stop sharing,
yeah,
and
exactly.
then
Stop sharing.
I go to the camera.
Perfect. Okay, great. So guys, ROS developers on the audience, think about a question for Andrei and put it on the chat, and I will transfer to him directly. So in the meantime that we are waiting for your questions because of this delay in the transmission, so let me ask you a question, Andrei. So can you tell us or explain us about any application of ROS2 being cross-compiled to another platform, so that you are aware, maybe in your own company or in other companies?
Yeah, so what we did, for instance, this year we did a demo. It's like a little bit more complicated demo. What we did, we have used Turtlebot as a platform, and we have used not Raspberry Pi but a similar ARM architecture with 4 cores, and we put underneath a hypervisor to show like a mixed critical use case. And then as a guest operating systems, we have put Linux and we have put a VxWorks, and on VxWorks it was a ROS stack running to show that all let's say real-time ROS2 applications can run on real-time operating system, which is VxWorks in this case, and all not real-time and non-safety can run on other operating systems, Linux. And this use case we have shown, so we have shown our application with the Turtlebot, whether you can control it from hands, or you can apply. It was a self-driving algorithm applied, and robot can run inside a particular area. and this kind of demos which were shown.
Okay, fair enough. And then I have another question, but let me go to the ones that are here on the chat. There is one by Integrity that says, Andrei, do you envision any challenges cross-compiling external ROS2 dependencies? Perhaps some libraries or subset of C++ which is not fully supported by VxWorks. So you mentioned a little bit that before, right?
Right. So thank you for this question. There are two aspects of that, right? So since like if you have not proprietary stuff, not proprietary operating system, then you don't have license issues. If you have proprietary operating system, then you might face license issues that some dependencies are not, let's say, have not friendly licenses, and you need to find a way to deal with that. You cannot just cross-compile. You can, even if you can compile them and run them on VxWorks, you would violate then proprietary source code because you put your stuff. And then, but for that, like we provide a version of VxWorks where you can use it in the user space, right? But another question is there are some limitations in the POSIX APIs, right? Even for instance, it is a ROS2 is a POSIX API. It could be that or can run on POSIX operating system. It could be that it would be not possible because some kernel calls are missing. In our particular case, for instance, we don't have fork and exec. We don't have some other functions. And if you try to cross-compile, you might have a problems with that. And you need to cope with this.
Exactly. Okay. Yeah, makes perfect sense.
And this is some kind of generic problem. It's not only VxWorks problem, but I think it's a generic problem for other operating systems, for cross-compilation.
Right. So I think that's the point that he, by Integrity, is trying to make about that. Okay, so we have another question here by Simon Krupinski that says, thanks, Andrei. What would be a good highly reduced selection of the ROS2 packages to cross-compile for running simple tutorials on an embedded computer? That's very cool.
Right. So we are discussing that, right? And actually, there is a discourse ROS2 forum, right? And I have raised this question. It's not at the moment is not possible so in an easy way. But I think I will be working on this during this year, and I will try to do this for Foxy release. First of all, probably just to run it on Raspberry Pi, just for or for whatever other hardware.
Okay.
But I will be working on this.
Okay, then I would suggest Simon to follow you closely. So when you have finished those tests and those setups, then he will be. So if he's following you, then he will know, and then he maybe will be able to get that set.
Yeah, and we also run. We also have this ROS2 real-time group. You can go and find us. And I'm preparing now not only like this, squeeze of ROS2 compilation, but also a possibility to run ROS2 in the real-time environment, in the real-time Linux, right?
Okay.
So it's, if you want this, please join us, and we will be happy to have you on board.
Exactly. As we are repeating around the whole conference, you are ROS developers listening to this conference, then you can contribute to any of the projects that are being presented here. Like, for example, the one of Andrei. Okay, so I think that is all. There are also a couple more questions there, but I think that we should stop right here. Yeah. And thank you again, Andrei, for your presentation. Thanks a lot.
I would send you, I would send the whole audience. Thank you so much. It's so long day, and I want to thank you guys. You have created really nice platform is so amazing that you can do like so cool stuff. And I really like learn a lot when I have started using this, and I have shown this this platform to my colleagues in the company, and they say like, wow. So good stuff.
Thank you very
so
much,
much,
Andrei. Our pleasure, our honor. Thank you very much,
you.
and see you around the world.
Yeah, thank you. Bye bye.
Bye bye.
Thank you. Bye bye. Okay, so let's continue the next speech. Before we start the next speech, let me remind you again to open the roadmap of our next speaker, the one of Oscar Lima. So you can find the roadmap link in your conference guide PDF. So please get ready with this roadmap. And so now it's time to have the fun. You already know it.
Yeah.
So we are going to play a video with a very specific topic about ROS. And the first one who answered the question in chat will win a I am ROS Developer t-shirt sponsored by eProsima and a coffee mug sponsored by Robotics company. So let's see the video then. Okay, welcome back, ROS Developers. Who is the winner?
Okay, so the winner is. It's getting difficult to decide for a winner. So I think that the winner is Florian Graham, okay, because his answer is clear and to the point. There is a previous answer from Shubham Garat, but it's very diffuse. We can work without having hardware remotely. We can work without having hardware remotely. It's not clear, that one. So Florian has made the point, enable students without hardware to work with hardware. Actually, it's enable anybody who wants to work with hardware that doesn't have the hardware to work with hardware. There are other answers afterwards, yes, that are also correct. Camila Perez, he said very clear also, access robots remotely. That's it. Remote robotics lab. So that's very, very clear. But unfortunately, Camila, so you were after that. And then, so congratulations, Florian Graham. That's your t-shirt and your mug. Okay, so
we are getting the next speaker ready. So remember to open the ROS chat of Oscar Lima.
Yes.
And here we still need some minutes for getting the speaker ready.
Okay,
so,
we got some problems with the speaker.
But just remember to open the ROS chat now, and in some minutes we will start with Oscar Lima.
And then remember that there are only 2 more speeches to finish the afternoon session. This one of Oscar Lima and the other one from Max Wittal about docking. This Oscar Lima is about ROSPlan, so how to make robots use AI planning systems inside ROS. It's quite interesting, that one, and is closely related to the one that we had this morning from Francisco Martin. And then this other in Francisco, it was using a complete intelligence system with planning, with tasks, and so on for ROS 2. And then ROSPlan is more focused on ROS 1. So that's one of the difference. And maybe Oscar is going to point us with other differences also, maybe. I don't know, we'll have to wait until we can have him here. And then remember, Oscar, then Max Wittal, then will be the coffee break, the second coffee break of today. And after the coffee break, we are going to go to the ROS Developers, ROS Awards, ROS
ceremony.
Awards ceremony, exactly, where we are going to deliver the prizes and the winners of the ROS Awards of this year.
Yes, it's an award for ROS and robotics, and we are going to give the prize for the best ROS software, the best ROS product, and the best ROS-based robot, and also for the best ROS developer.
Exactly.
Okay. So stay tuned for this ceremony. Yeah. And so we are getting the Oscar.
Still some problems in there. And this, let me tell you about the ROS Awards. This is the first year that we are doing these awards. Yes. And the goal of the ROS Awards is to provide some visibility, to all those people that are working very, very hard to make ROS better in all those aspects that Johan has mentioned, about developing, maybe about creating products, creating software packages, creating robots, and so on. So we want them to have visibility, okay? That's the purpose. And for that is the ROS Awards.
Yes.
So we have to wait and a little bit for that. Then in the meantime, so let me tell you about the quizzes, okay? So it's a little bit difficult, okay, it's getting a little bit difficult to provide you a winner for that, because especially if the question is a little bit open like this one, then I think that in that case you will have to trust our decision, because of course we don't have any interest in anybody that on the chat, so for any special interest in winning, so it's our it's our interest. So it's our how to say, so it's really our criteria that is going to decide, and is based just in what we feel on that moment. So sorry, yeah, maybe there is no very clear cut in those guys, but that's also how life is.
But don't worry, we will have one more quiz again after the speech of Oscar Lima.
Yeah.
So stay tuned and have this chance to get the answer and try to win the ROS Developer t-shirt and the coffee mug.
Exactly. There is a movement that has been started by Gabi Gallegos on the chat that is saying about t-shirts for all, and then that's a very nice movement. So I can tell you that this is not possible this year, but we are going to think for the next year conference. Remember that this is the third year that we are organizing this conference, and it's going to continue forever. So as far as we are alive, then we are going to keep continuing. And always has been the interest of this conference is to be online. Okay, why to be online? So to be online because then anybody can attend to the conference, and because you don't have to travel. So you only have to be at some location, at your location, and then connect. That's very cool. And there is a problem of the times. So we don't know about the times that different for the different zones.
Yeah.
Then there is a time zone difference in that maybe for some people is more convenient, for some others is not as much convenient. Then in this case we selected more or less a time for here in based on Central Europe in the early morning, because we started in the early morning here in order to be like in all places, you know. In Asia is getting late. It's getting and then in the America is getting in the morning. In the morning, it's starting to be. But and some places then could be 2 a.m. There were some people on the audience that were at 2 a.m. and then that's very funny. So we are experimenting with different types, and we'll see. We accept suggestions, okay? But don't say the best time for me. So provide us with some suggestions for the whole audience, okay? Think about that. And so do we have the speaker ready?
Yes, we have the next speaker ready. So let's welcome our next speaker, Oscar Lima. Oscar is a researcher from DFKI, which is the German Research Center for Artificial Intelligence. One of his lines of research is AI planning applied to robots.
Yeah, and in his talk, so it's going to, as I mentioned before, Oscar is going to show us how to apply ROSPlan to ROS robots, which means that he's going to show us how to use AI planners into ROS robots. So you can introduce their AI planners into the world of ROS. So welcome to the conference, Oscar. Are you ready?
Yes, hello.
Okay, great. We can hear you. And if you are ready, then the audience is all yours.
Perfect. Hi, everyone. So my name is Oscar. Thank you for the nice introduction. Like they said, I mean, I work at the DFKI, which is a German Research Center for Artificial Intelligence. We have more than 5 research centers here in Germany. 2 of them are focused on robotics, and the other ones are focused on other aspects of artificial intelligence. So a little bit about me. I mean, who am I? I have more than 7 years of experience with ROS1, which is sadly coming to an end in 2025 with the last distribution, which is Neobotix. And I'm a number 3 ROSPlan contributor. So now I will proceed to share my screen, and let's start getting some hands-on on ROSPlan. Yeah. So what is ROSPlan? So ROSPlan is a framework that provides a generic method for task planning in a ROS system. So in this talk, I will assume that you have no knowledge about task planning, and I will cover so everything step by step and the basics. Just a small disclaimer here. So ROSPlan is a tool that was created by King's College London University, KCL. So DFKI did not create ROSPlan, of course, but we contribute from time to time to its development. So this talk is about how to integrate ROSPlan into your robot and get a little bit of hands-on on ROSPlan for you to see what this is about. So what is ROSPlan? So ROSPlan is useful and will enable your agent with decision-making and plan execution capabilities. So this is, you have an environment, you have a robot. The robot perceives the environment with its sensors, and then it transforms this sensor data into symbols, which in task planning, we refer to symbols as strings, basically. So, for instance, this could be the fact that the robot is in the kitchen. So via some localization algorithm like particle filter or Kalman filter, we know that we are at a certain X and Y position and orientation. And since this position is inside some region which we named kitchen during some semantic mapping step, which is not part of ROSPlan. So this is one step before you have to provide with this environment representation algorithm. So this will add to a knowledge base the fact that the robot is in the kitchen. So this is this first step, which is perceiving the environment, transforming this sensor data into meaningful data, and store this in the knowledge base. So ROSPlan provides a knowledge base for that, which is a symbolic knowledge base. We have several actually. So we have one for PDDL, one for RDDL, and hopefully in future we will also have some other supports for other planners. So the second step is you receive a command from the user. So the user speaks to the robot like fetch me a bottle of water or something like that. And then there has to be a pipeline outside of ROSPlan that transforms the audio from the person into a string. And then this string needs to be converted into some sort of natural language understanding. And the output of this natural language understanding should be like a goal to our system. And this is where ROSPlan receives that goal. And based on the current state of the environment and the goal, it will make a plan for you. And it will dispatch this plan so that the robot can execute it. So a plan, I mean, the simplest definition of plan is a sequence of actions that the robot needs to follow to achieve a certain goal. And the simplest executor that we could think about is to take this plan and execute its actions one by one. I mean, ROSPlan provides a more complex dispatch node, which you can also use, which is the sterile plan dispatch, but we'll get into that later. So what are you going to learn about? So you will learn a little bit about PDDL. So what is PDDL, what PDDL stands for, how to model problems in the PDDL, how to describe initial state and the dynamics, the physics of the world in PDDL. Some basic symbolic knowledge representation, as like I said a little bit before. So this could be the fact that the robot is at the kitchen, or the fact that we have 2 or 3 robots in the environment, the fact that a bottle of water is on top of a kitchen table or something like that. And then we have the plan generation. So for this we need a planner, so an AI planner. So it turns out that there are many planners out there, thanks to the international planning competition. So we will talk a little bit about this later. So basically, ROSPlan can be think of a wrapper of planners, AI planners, so that you can easily integrate them and make them to generate plans for your robot. Yeah. So the next step is plan execution. So the complex, fancy way to do this is using the stereo plan dispatch, which is a graph representation of the plan. So you transform the plan into a graph, and then you execute the graph. But yeah, we will see this later. And you will learn also about a little bit of the ROSPlan architecture. So which nodes are there, how do they communicate with each other, and how to call their services, which services do they provide, right? So this is done in the context of a demo. So the demo that we have for you uses the Turtlebot 3 robot. We have many other demos, but for this tutorial, we will only cover this demo here. So I already presented myself. Who am I? I'm going to skip this now. So let's start with the introduction. So what is task planning? Task planning is useful for decision making. So we want our robots to think about the task that they have at hand, and we want them to reason about how to solve this problem. So this is a kind of some sort of like intelligent behavior, so where the robot needs to think about what to do. And typically in robotics, I mean, people solve this problem usually by using state machines. So, but we can do much better. So as an improvement of using state machines, we have several other ways to make decision-making robotics. One of them is task planning, which is the one that covers ROSPlan. The others as well, like for example, behavior trees. You have also Petri nets, and you also have some approaches related with machine learning, like reinforcement learning, for instance. Yeah, so task planning in general, it's a tool for generic problem solving. And when I say generic, I mean really generic. I mean, it's task planning was not created for robotics. It was created for all sort of problems. So PADL is used, for instance, in helping to protect the system from hackers. So this is one of the applications of a PDDL. It could be used. Another practical application that I know of is they try to automate the oil extraction process, which is performed by engineers at Schlumberger. So this is another example, but just to get you the idea that task planning and PDL is a tool for generic problem solving. It can solve any problem that you put, not only robotics. So what does PDL stands for? It's the Planning Domain Definition Language. So this comes back, I mean, now a little bit of history. So it all started with strips. So this is the Stanford Research Institute problem solver, which was probably the first planner that appeared out there, which was somewhere in the 70s with the shaky robot. And then it evolved into the action description language, ADL, in the 80s, roughly. And then PDL was created in 1998. And this was done as an attempt to standardize the input for AI planners. So because the international planning competition, the first international planning competition was celebrated in 1998, and they have multiple planners which they wanted to benchmark all of these planners and see how they performed with respect to each other in terms of time, or in terms of optimality, or in terms of how much CPU they use. This could be some sort of like benchmark criteria for the planners. So in order to standardize these planners, so PDDL was created. And in short, I mean, PDL is just a language to describe problems, task planning problems. So why is PDL important? So PDL is one of the main input languages in ROSPlan. So we have support for plain PDDL, because I mean, even in PDDL there are like several versions of PDDL. Probably one very nice reference that you could consult is the Wikipedia page for PDDL. It's actually quite good. So it describes all the versions of PDDL, so 1.2, 2.1, and so on. So the most famous ones are plain PDDL, which is 1.2. This is more like a classical planning approach. Then you have PDDL 2.1, which is related to temporal planning. So it brings temporal actions into the picture. So now the actions have a duration, start and an end, and you can specify preconditions at start, preconditions at the end, and preconditions during the action. And more newer versions of PDDL nowadays in the community is PDDL Plus, which brings some nice stuff like event support for events, and like the use of continuous variables. Yeah, so the thing is that to use ROSPlan, you have to know how to model in PDDL language. So you really need to dig into this. Yeah, so some assumptions of PDDL, because I mean the problem we are dealing is actually very, very hard. So it's NP hard. It's not searchable in polynomial time. So typically what you do is you start with one node, which is the empty node, let's say. I mean, there are many approaches, but the general idea is that you look at the actions that your robot can do, and then from there you just make a tree, let's say, at the beginning with all the actions that your robot can do. So if your robot can do 5 actions, your tree will have a branching factor at the beginning of 5. And then if you have chosen the first action, then your tree can further decompose into more actions and so on. So this will at the end will create a graph, and searching through this graph is what the planners do to make a solution. So because this graph cannot be searched in polynomial time, so it's an NP hard problem. Task planning in general makes some assumptions about the world. So in the most basic version of PDDL, so you have node time. So these are some of the assumptions of PDDL 1.2. So you have no time, no events. This means that you create a plan offline, and if something happens during execution, you cannot react towards that thing that is happening. So this is also called exogenous events, they call them. You have a discrete representation. So this is usually referred as snap actions. So you execute an action and it takes one instant of time. So you cannot have like a continuous falling of a ball, let's say. Yeah, so you also have a deterministic action outcome. So this goes against the MDPs. So whoever of you is familiar with a Markov decision process. So in Markov decision process, what you have is the robot executes an action and you have a certain probability of success, which is not 100%. I mean, it could be anything, but let's imagine is 70% of probability of this action being successful, but you have a 30% of probability of not being successful, which will lead you to another state. And as you can imagine, this makes the graph grow much bigger. So MDP planning it's also out there in the community, and ROSPlan supports a little bit of this type of planning. So we have integrated through the nice work of Gerard Canal. During an internship at KCL, he developed the interface for RDDL. So this is with the Prost planner, and it's related with probabilistic planning, but we will not cover this in this tutorial for today. Yeah, so the next assumption is that the environment is fully observable. This is not always true, but let's say if you have full control of the environment and you put sensors everywhere such that you make the environment observable, then this condition remains true. And in PDL, you have a goal state condition, so a set of predicates that you want the system to make true, instead of, for example, in hierarchical task networks where you have a set of tasks to be accomplished. So yeah. So let's see. Let's talk about the PDL solvers, so planners. So what kind of planners can we find out there? So the International Planning Competition actually requires that all planners that participate in this competition to release the source code after competing. So this is actually quite nice because every time there is an international planning competition, you have a set of planners, open source planners that you can try out. So the last IPC, if I remember correctly, was in 2018. And before that, it was in 2014. So you have a collection of planners there available to the community throughout many years of research in the AI community. So ROSPlan supports many of these planners. We will talk about this later, but by default, we use the POP-F, which is a temporal planner. And we, yeah, I mean, the only thing that changes when you try to use a different planner is the parsing interface. So the parsing interface, we have many planner interface in ROSPlan, such as FF. And let's just quickly go to see what kind of planning interface we have there. So this is the main ROSPlan GitHub repository, github.com, KCL planning ROSPlan. And if you go to ROSPlan planning systems and then SRC plan parsing, no, it's not plan parsing, it's planner interface. So these are the planners that are currently supported. So you have the FDP, the FF and FFHA planner, which is very famous planner from that won the IPC in 2002. You have LPG, POP-F, as I mentioned, and some others like SMT. SMT is actually a planner that was created by the creator of ROSPlan, so it's by Michael Cashmore. It's a PDL plus planner. Yeah, so this is the standard diagram of how a PDL solver looks like. So the planner receives two inputs. So you receive a domain definition. So this domain definition is a file, domain.pdl file, which describes the physics of your environment. So if you execute a certain action, how will the world look like afterwards? So this is basically the main idea. And then the second input to the planner is the problem. So the problem at hand describes a particular situation. So you instantiate some robots, you instantiate some objects and some locations in the environment, and then the problem becomes a specific problem that you have at a particular point in time. And then the planner takes these two inputs and produces a plan, which then will get executed. So much for explanation and talking. Let's actually get some hands-on. So let's launch the simulation. And to do that, we need to open a terminal, just like I did here. And then in this terminal, we wait for connection. And we will execute the following commands here. So the first one is just sourcing your cutting workspace. And sourcing your cutting workspace has been already added to the .bashrc of the ROS project. So you don't need to execute this first line of code. Then the second one is just the selection of the robot. So in this case, we will select the toolbot tree, the waffle specifically configuration. And then afterwards, we launch the main toolbot.launch sample file. Yeah.
Okay, Oscar. Yes, it looks like the terminal is doing again his magic. Then don't worry. So it's going to connect. Just wait a little bit for that, and it's going to yes. So maybe we can move forward while it's going to appear.
Okay. Yeah. Sure. Oh.
There it is.
Perfect. Just in time. All right. So then I copied this command to export this environment variable, which will tell the system to use the waffle configuration of the toolbot tree. And then we copy this other command here, which launches all required components. So it will launch the simulation, gazebo, RVs, ROSPlan, and all the nodes inside ROSPlan that are required for this demonstration. We wait a little bit until it finishes launching all the stuff. And afterwards, we will need a second terminal. And before we run the command, let's go to simulations and start simulation. So there's another way of doing this as I was told, which is here. So tools and gazebo. So whichever one you prefer, I will use this one. And then you get access to the gazebo GUI. So now the simulation is starting. You have simulation log here, which pops out the robot and the environment. So if you see that the environment lacks color, you can just use this refresh button here, which will load again the gazebo, and the textures now are there, some of them. And yeah, so the next step is to open RVs. So for opening RVs, you have to go here to Tools and Graphical Tools. And when you click on Graphical Tools, then you will get access to all these RQT interfaces that you launch, such as RVs. So here we have RVs and the toolbot tree and the environment. So this is a top view, 2D of the environment. So this is already running a navigation stack on the background, which is move based. So let's center the robot actually. So to center the robot, we click here on 2D navigation goal, and then we give some goal to the robot. The robot should start moving towards that goal that it was given to him. You see that the particle filter is doing its job and narrowing down the particles to localize the robot. And then afterwards, we are ready to launch our simulation. So the next step is to do ROSRun, ROSPlan, toolbot tree demo, explore.bash. So when you do that, a lot of services are being called, and ROSPlan is calling all the pipeline. So the robots start moving, and we can see this also in RV's window. So in RV's, you see that a graph is being generated, and the robot is now traversing this graph. So these are two waypoints that the robot needs to visit. Yeah. So looks like a successful demo. So the robot went to waypoint 1, and then after finishing, it went to waypoint 2. And it's important to mention here that, I mean, we have two dependencies for this demo. We depend on the ClearPath Robotics occupancy grid utils, and we also depend on MoveBase. And MoveBase has a certain probability of success, which is not 100%, but it's quite high in my experience. And also the occupancy grid utils will try to find a free space inside the map. But sometimes when the waypoints are very close to the obstacles, then the demo will fail. So if this happens to you, don't worry, just you will have to go to this terminal, kill the process, launch it again, and then hopefully the second time we launch it, it will be successful. So we know it's successful because here it says success true, goal achieved true, and then it says finished. So yeah, let's go back to the notebook to see what's going on, what happened, and try to break down a little bit the stuff that happened in the background. So this is what happened. So the robot should now explore the environment. So it has generated a graph. So this graph is generated actually during runtime. So the robot is not given with this graph beforehand, but it subscribed to the map. And by subscribing to the map, it knows where the obstacles are in the environment, and then it generates free collision waypoints inside the map, and then it stores these waypoints in the parameter server, and then what ROSPlan does, it makes a plan to explore these waypoints, and then queries the waypoints. Because ROSPlan only knows about symbols, so ROSPlan knows WP1 and so on. Yeah, but let's go step by step. So in the high-level explanation of the demo, so we have the main three components, which is the Turtlebot tree simulation in Gazebo 9 and ROS Melodic. The second one is, also the MoveBase, so Turtlebot simulation plus MoveBase. Second, we have the roadmap, which is the random waypoint generation. This is what will allow us to explore the environment. And this is the one that I mentioned. It was from ClearPath Robotics. And the third component is ROSPlan, and the ROSPlan architecture that will do many things we will see. So going a little bit more in detail of these three main points. So the first point is the Turtlebot tree simulation in Gazebo 9. So this is what I talked about. So ROSPlan knows about waypoint 1, waypoint 2. So these are just the strings or symbols as they are called in task planning. So the waypoint has a symbolic and sub-symbolic. So sub-symbolic is just the mapping of this numeric data. So sub-symbolic is numeric data, numbers or pairs of numbers. And symbolic is the strings. So we have to make this mapping between strings and the numbers. And in this demo, this is done via the parameter server. So because MoveBase sends the robot to a particular location using pose, so position plus orientation. In this case, orientation is expressed in quaternion. So let's try and query this mapping. So if you copy this instruction here, then this actually queries the parameter server. So this parameter here, ROSPlan demo waypoints, waypoint 0, it's information which is stored in parameter server, and by executing this command, you get the information behind this waypoint, which is in the form of X, Y, and heading, so theta. And then, so the second one is the roadmap. So I put here the link to the repository from ClearPath Robotics. So we are using this as dependency, as already mentioned. And this will generate random free collision poses in a given a known map. So it will subscribe to the map. And last but not least, ROSPlan in the context of this demo will provide with the following nodes. So it will provide with the knowledge base where all this symbolic information is stored. It will provide with the problem interface. So what the problem interface does, it queries the knowledge base for information, and it will automatically generate the PDL problem for you. If you remember this diagram that I presented to you. So this problem is generated during runtime by this node that I explained below. And the domain is static. So this is a file that you as a robotics modeling expert need to make one time only, and then it will not change afterwards. And then let's see. So the next step in the pipeline is the ROSPlan planner interface. So this one is the one that provides input to the planner, so the domain and problem, and runs the planner to get the solution. And the solution is returned to the ROSPlan system in the form of a string, actually. So this is something like running the planner on a terminal and looking at the string that it provides for you as a solution. So this string needs to be parsed, actually, for finding if the plan was solved, or if the solution was found or not. And if the solution was found, then what are the steps in the plan? So we need to parse this string to extract this information in a computer readable format. And this is what the ROSPlan parsing interface is doing for you. And as you can see, the parsing interface is actually dependent on the planner. So different planners will output different strings. And this is why we have different planner interfaces. So that they can attach to the particular output of that planner. Yeah. And finally, we have the ROSPlan plan dispatcher. And what the dispatcher will do, it will subscribe to the plan, which is already parsed for you. And it will either execute sequentially in the most simplest way, or if you select the sterile plan dispatch, which is the default one in ROSPlan, this will transform your plan into some sort of STN, which is a graph, and then it will execute the plan in a graph manner. So then you have related documentation here available. So this is the ROSPlan website. So here we have some tutorials that you can follow. If you want to go step by step, you can follow the tutorial one for problem generation. Then we have another tutorial for the planning part, one tutorial for plan execution, and so on. So we have many information here and some nice diagrams of the stuff that I just explained to you. So this one at the top is actually, you can see whole ROSPlan at once. So you have the knowledge base, and then if we go in sequence, the problem generator, the planner interface, this will communicate with the planner and get its output, parsing that output, and then dispatching the plan to execute into a real robot or simulated robot. So definitely check out this page offline with more time. And let's continue. So if we go even a little bit more in detail. Yeah, so here I have put the PDL domain definition of the Turtlebot demo, which is the one that we are running. So you can see here that we have defined the domain, we have defined some requirements. So this is just any name will do fine here. Then you specify the types. So these are sort of like your entities of your work. So here you will put, for instance, objects, robot arms. You will put like vehicles or trees or whatever entity you have in your world. So in our world for this demonstration, we have only two entities or two types, which is one robot and multiple waypoints. And all that is left is to specify instances of these types. So these are like containers. And this goes actually into the problem. So in the problem description, we will have one instance of robot, which is robot 3, and multiple instances of waypoint, which we call waypoint 0, waypoint 2, and so on. Then you have the predicates. The predicates are actually statements of your world, so which statements are true in your world. And to fully describe our world, we just have 3 predicates. So this is robot at, and this describes the fact that the robot is at somewhere. So this an instance of this container, let's say, could be robot at to robot 3 and then waypoint 0. And if you have this predicate, it means that the robot is at the waypoint 0, located at waypoint 0 from a semantic perspective. And then when you go to the parameter server and then you do the mapping of the symbolic to sub-symbolic, then you get the pose of the robot. So the second predicate is connected. So we use this predicate to express the fact that there is a path between 2 particular waypoints in the map. And we have a third predicate, which is called visited. So this is the one that we use for making the goals. So in the problem definition, as a goal, we put the fact that waypoint 0 needs to be visited and the fact that waypoint 1 needs to be visited. And this will effectively trigger the plan generation for us. And then we have some functions. So we have a way to specify a distance between the waypoints so that the planner will try to make some heuristics to plan. So the heuristics differ from planner to planner. But just to give you some examples, it could be like minimize the energy that the robot will spend, or minimize a certain cost, and each action could have a certain cost. So you can define, for instance, if you want a navigation action to be expensive or cheap, and perception action to be as well, like expensive or cheap. And you do this by assigning an integer number. So every time you perceive something, you increase a particular value. And last, we have the definition of the actions. So this domain is, of course, very simple. This just has one action, which is go to waypoint. So here you could have more complex actions like perceive object or grasp object or open gripper or something like that.
Oscar, 5 minutes to finish.
Yeah. Oh, okay. And yeah, let's try to speed up. So, I mean, if you want to play a little bit more with PDL, I can recommend you a very nice resource, which is you go here and you type https://planning.wiki/ref. And this is actually a very, very, very nice website. If you are new to PDL and you want to get more deep into PDL and all the different versions of PDL, this website is definitely the one for you. And yeah, so what this bash script that we run here is basically doing, it will call multiple services automatically for you. So the first service is to create the waypoints. So this one communicates with the interface from ClearPath Robotics, and it will generate the probabilistic roadmap for you. Second one, it adds the initial state and goes to knowledge base. So the fact that the robot is at waypoint 0, the fact that there is one robot which is called Turtlebot, and the distance between the waypoints and so on. And then it calls sequentially all of these services. So it's really not that complex. I mean, if we go back to the graph, here every node, so the problem interface is offered as a node, the planner interface is another node, parsing interface another node, and plan dispatch another node. And what the script does, it calls services one by one. So it calls the service for generating the problem, service for generating the planner, service for parsing the planner, and service for dispatching the plan. And another very nice thing that I recommend you to do is to copy and paste this command in the terminal. And what this command will do, if you go back to the RBase window, where we can see our GUIs, here ROSPlan provides with several GUI interfaces, such as this one. So this one allows you to visualize the knowledge base. So the knowledge base is basically divided in 4. And here you have all the entities of the world. So 2 waypoints, 1 robot. Here you have the facts. So waypoint 1 is visited because we already have visited. Robot is at waypoint 1, and waypoint 0 is connected to waypoint 1. Waypoint 1 is connected to waypoint 0. And here are the mission goals, which is to visit waypoint 1. So this allows you to remove goals, actually, or to add new goals. So here we could add the fact that we want the waypoint 1 to be visited. We add the goal, and then we are ready to plan. Of course, we will need to remove these facts here. Yeah, so this looks like a problem that the planner could handle. And so we have another command, which is the just to finish. I'm finishing actually. So there is this command which allows you to run the serial plan dispatch RQT interface. And then we will go back to our GUI interface. And this is another nice GUI that ROSPlan provides, which allows you to visualize a plan. So this is the plan that was generated by PopF. And these are the steps that the road needs to execute. And this graph is actually updated during runtime. So the nodes which are finished will appear in green. If they are unfinished, they will appear in yellow. So you can track the state of your execution by using this tool. And yeah, so here I put the problem that was generated. If you are curious, you can see it. And yeah, so the last thing that I would like to talk about is this ROSPlan to robot example detailed PDF document that I have made for this. Actually, I had it earlier already, but it suits quite well to this tutorial. So here I have all the nodes that are included in this demonstration. And here I put arrows to all of the information, exchange of information that is going on between them. So the problem interface outputs on a topic this information here. The planner interface receives this information and produces this information here, so the plan. And then the plan is received by the parsing interface and produces a graph, which is the plan. And this graph, it's published to the stereo RKT, which allows you to visualize the plan and the plan execution. And at the same time, it will call the action lib interface to effectively perform your action in a ROS system. And with that, I think I will finish. Yeah.
Okay, great. Perfect. Thank you very much, Oscar, for your presentation and your explanation and demonstration about the ROSPlan, this planner for AI, introducing AI planners into ROS. That's great. Thank you very much. Can you switch to your camera so we can see you with, now it's time for the questions. Great. Hello. And so now it's time for the questions for Oscar. So you know the procedure because, I mean, we have been here the whole day. So you know, you have to write your questions on the chat beside the video, and then I will pass them to Oscar just through here so everybody can hear and listen the questions and the answers. So let's go with the first one because there is already one on the chat that was written before everything, and then he's from Francisco Martin Rico. Probably you know him, and was another of the speakers of the this morning. And he says, one question to Oscar Lima. Are you considering starting to use and contribute to ROS2 planning system, the Plan SIS2? That this is the one that he has presented this morning, and then it would be fantastic to work together. So what do you think about that?
Yes, so there have been some discussion actually in ROSPlan to migrate it because it's currently in Melodic and ROS1. And of course, ROS1 is dying, so we need to shift to ROS2 gradually. I mean, in the next 5 years, let's say, we need to do that. Maybe earlier, in the next 3 years.
Okay.
And definitely, we also want to first migrate from ROS Melodic to ROS Noetic, and we also have plans to migrate to ROS2. This, of course, I mean, the main constraint is time. Because I mean, here at the institute, we dedicate only a small amount of time to do ROSPlan stuff. So we are strongly biased towards HTM planning, actually, which is currently not supported in ROSPlan. And we would like to sort of create some version of ROSPlan which supports HTM, and of course this in a ROS2 environment. But this is like a long-term goal, and I think our efforts are more towards that direction.
Okay, and do you know about Francisco? So do you know him, Francisco Martin?
Not personally, but I have seen him in the GitHub. So he's active or was an active ROSPlan contributor. Yes.
Okay. Then you can be in contact easily then. Okay. Then let me go to another
Definitely.
one. Okay. Great. Let me go with another very short question from Michael Terther that says, is there an example of how to use ROSPlan with behavior trees?
No, so ROSPlan does not support behavior trees, and therefore no example.
Okay.
Sorry.
Okay. Yes. Well, it depends on the implementation and many things. So of course, understandable. Then another question, last one for you, is from Frank Imeson that says, question is, PDDL 1.0 was PE space complete. What steps does ROSPlan take to reduce the search space size?
It's not so much about ROSPlan, I would say. So this depends on the planner. And in ROSPlan, what we try to do is integrate existing planners, but not so much, it's not the focus to create new planners. I mean, planners, there are a lot out there. And yeah, so the idea is to take these planners and execute the output that they produce, and how to try to make them as compatible as possible, because the output that those planners produce is different. And at the end, we want to have a common execution architecture that could capture all this diversity of output that they produce and be executed in a common way.
Okay. And then actually anybody can create his own planner and then introduce inside ROSPlan, right?
Yes. So typically, I mean, you can create your own planner, and you can just create a planner interface for it. It would be straightforward to do. But usually also what is recommended is to go to the international planning competition and see what planners are there. And of course, you want to maybe have the best planner available.
Exactly. Yeah.
The state of the art, the best that is out there.
Exactly.
But how to know that? Because you have to objectively compare their outputs and see how they perform. And this is exactly what the international planning competition is doing for you. It's doing this benchmark for you, and it's done in a research fashion, objectively. And they are given with the same amount of problems, with the same complexity. There are strict rules about the time that they have to produce a solution, and so the output of the IPC is, or it already tells you out of the box which is the best planner in which category.
Okay, great. Okay, so then there are no more questions, but there is no more time because we are running late. Yeah. Then we are going to stop here, and thank you again, Oscar Lima, for your presentation. Thank you very much.
Thank you.
Yeah, most welcome. My pleasure.
Bye.
Bye.
See you around the world.
See you.
See you.
Ricardo, we're about to start the final speech.
Yes. Of the ROS Developers Day.
To the last moment already, almost there.
Yes.
So please remember to get this last roadmap open in your conference guide. And for the next speech, we will have Max Wittal. Please get ready this roadmap in order to practice with Max. So before that, we will have the final quiz again now.
Exactly.
So we are going to play a video, as you know. You are going to answer the question based this video. So let's see the question.
Hello, welcome back, and then let's go to this winner of the last quiz video that we have. And there, what happened? So the energy went low, or you just don't want to say anything else because somebody else maybe has said correctly? So there were less answers. Okay, so no problem. But anyway, one of the answers was the correct one, and it's the one from Aditya Kamath. So the project is AutoWare Auto. Okay, so that's the response. So it's the implementation in ROS2 of the self-driving stack. So congratulations, and our team is going to contact you for delivering the map that is sponsored by Robotnik, and a t-shirt that is sponsored by eProsima.
Okay, congratulations. So now let's welcome our final speaker. It's Max Wittal, software engineer at the Neobotix company. Max is an expert in ROS and in autonomous car, and today he's going to teach us about a very important skill of autonomous car. Is about the docking behavior.
Exactly, the docking behavior is this behavior that allows the robot to go and self-connect by itself to the charging station. So, you know, that's very important because the robot is detecting that it's running out of batteries, then it can go to the charging station location and then connect to those plugs that are there. And he's going to present us the Neo docking package. That is a package they have developed at Neobotix and can be used with different robots. And he is going to show us how to use this Neo docking package by using a camera, also a point cloud, and a navigation system. So let's see if Max is ready for the speech. Are you ready, Max?
Yes, I'm ready.
Okay, very good. So here the audience is all yours.
All right. Thank you very much, Ricardo and Yohong, for the introduction. And hello, everybody who's listening. I hope you had a great time so far. Should we go to the notebook already? Or?
Yes, you can go directly to the notebook and share your screen.
Let's begin. Oh yeah, sorry. Let me share my screen. All right. So can you see the notebook?
Yes, it's there.
All right. So today, like Ricardo already introduced, we want to show you our new docking package, which allows you to dock your robot using visual feedback, for example, like from a camera. And the agenda for our talk will be a small introduction of our company and myself, and then we will take a look at the robot, the MPO 700, which you can see down here, which we will be using today in the simulation. And then we will take a look at our Neo docking package, and finally we give you some takeaways. All right. So first, a little bit about myself. I'm Max Wittal from Neobotix GmbH. I'm the ROS software development lead, and we are sitting right now in Heilbronn, Germany. Before that, I used to develop autonomous driving software at Daimler/Mercedes in Silicon Valley. And in general, I'm mostly a C++ developer, and I've done a lot of work in CUDA and image processing. And now recently, I joined the robotics industry. And in my own time, I also do some electronics. Yeah, mostly as a hobby. All right, let's go a little bit to our company, Neobotix. We are a spin-off from the Fraunhofer Research Institute in Stuttgart. We've been working on some of the earliest autonomous mobile robots in Germany, like the first Carobot generation back in 1998. Since then, our focus has always been on mobile robots and mobile manipulators for research customers. Our strength is in customized robot systems based on our standard platforms. Besides integrating different robot arms and other devices, we also design completely new robots with unique specifications. And our main area of expertise are in omnidirectional robots that can move instantaneously into any direction. For example, the MPO 500 with mechanism wheels and the MPO 700 with our own OmniDrive modules. We will be using the MPO 700 in our webinar today. All right. Let me quickly introduce our new templates that the construct created for us. Thank you very much. You can see our MPO 700 already loaded in the simulation, which is really nice. And we further look forward to extending our partnership. Okay. Now let me introduce the contributors to the package, which is mainly Sihao He, which is a former intern of ours. He's studying at the Karlsruhe Institute of Technology in Germany, and he did most of the work. It was his project for his internship. And myself, I was helping him in his development. And Pratip Krishna, he's our current master thesis student from the Hochschule Bonn-Rhein-Sieg in Germany. He was also helping Sihao, and also he created the entire ROS check, and he's our simulation expert. I thank him very much. All right, let's check out the robot, the MPO 700. It's a non-holonomic omnidirectional mobile robot. It has 4 OmniDrive modules, each with 2 motors for steering and traction. It's our platform of choice for high-end service robots because it has a high payload capacity of up to 400 kg in total, in combination with a high maneuverability. Regarding safety sensors, we usually equip 2 SIG laser scanners, for example. And also we offer additional sensors like ultrasonic sensors and like a 3D camera, which we will see today. Down here, we see the first MPO 700 used at the Fraunhofer IPA for the CareRobot 3. You can see in the back here, it's one of the drive modules, and you can see the SIG laser scanner up here. And usually we sell the MPO 700 in combination with a manipulator, for example, a UR10 from Universal Robots. Yeah, it's the biggest manipulator I think we currently offer on the MPO 700. All right. Let's take a quick look at autonomous docking in general. So the process of automatically connecting to various hardware for purposes such as automatic charging, which we will see today, but also transportation of a trolley is another common application. And yeah, the most common places where the docking is performed are in hospitals, warehouses, and manufacturing industries. And in general, the goals of auto docking are reducing the physical stress on the operators, providing a scalable solution for common tasks. And also docking by hand is quite difficult if you've ever tried it. Yeah. All right, and at this point, I want to show you our latest video that we just finished yesterday. Let me quickly copy this link. And I guess I have to stop this screen share real quick and then go to YouTube.
Max, we cannot hear you talking. We can hear the... Hey, Max. Max, we cannot hear you talking. We can hear the video, but not you. You are muted. Yeah, I don't know. You can.
Oh, sorry.
Now.
Can you hear me now?
Now,
Ah, yeah.
yes.
It seems like it
And the
automatically muted.
video, can you put the sound a little bit lower
Oh,
so we
yeah.
can hear you better because the music is very loud.
Let me see if I can do that here. It doesn't seem like I can disable the sound in the video. Maybe just watch the video and then I will explain a little bit.
Okay, perfect.
Oh, I guess it finished early. Let me try that.
Hear you.
Yeah. Let me try that again.
We cannot hear you.
Okay. Can you hear me now?
Yes.
All right. I guess the video finished a little bit early. I don't know why, but in any case, I hope you saw the docking process at least once in the video. It also mentioned that it is a three-stage docking process. So we have 3 stages, and at each stage we take a new measurement and we move one step further. And at every step we get a more accurate estimation of the marker position. And in the final step you can see then it gets very accurate. Am I sharing my screen right now?
Yes, go ahead. We can barely hear you because of the music.
Oh, the music is still playing? Oh.
Okay.
Oh, I see. I thought I stopped the video. Could you hear me what I just said?
Yes. Yes.
Okay. Okay, let me switch back to the screen sharing.
Sure.
Okay. Let's go back to the notebook. Okay, now we will take a quick look at the simulation package, how the architecture is laid out there. So, of course, we use Gazebo, and we have here the ROS control of Gazebo, which includes the hardware interface, which we use the simple transmission, and of course the joints and actuators. And in the URDF, we have the robot model of our MPO 700 and all the attachments. And up here we have the MPO 700 kinematics, which is the same as in the real case. And down here we have some controllers for the simulation, which simulate the motors, and of course a robot state publisher, so we can see what's happening in Avis. All right. Now we can introduce our new docking package. Our new docking package can be used for automated charging of our robots, for example. Apart from that, it also has a modularity, which provides the option for extending it to other applications, such as automated docking of a supply cart or to a conveyor belt. Let's take a look at the software architecture of the new docking package. So up here we have the MPO 700 simulation, which you just saw above, which, for example, provides us the point cloud, which is then used by the AR track Alva node to detect the marker and also estimate the 3D position and rotation, which was then published on a topic called AR post marker, which is then used by our auto docking node, which can be triggered by the user by calling the auto-docking service. And inside the auto-docking node, we also have the move base, which is also using our new local planner, which then computes the command velocities to control the robot. Okay, let's take a closer look at the auto-docking package, as I would say node. Down here, we have the AR pose alva node giving us the AR pose marker information, which is the 3D position and orientation, which we then first we transform it to an odometry frame, so we can apply a sliding window filter to get a more accurate and robust estimation of the marker, which is then used by the docking function to forward it to MoveBase, which is using our Neo local planner, which is then outputting the command velocities for the different stages. Yeah, and I have to say that without our Neo local planner, we wouldn't be able to use MoveBase for this. But since we have it and it's quite accurate, we realized that we can just use MoveBase for the docking process. And this way we don't have to duplicate all the work that goes into controlling a more complex robot like the MPO 700. So we don't have to do that twice. We just use MoveBase. Yeah. All right, let's go a little bit further into the tags we were using. There are so-called AR tags. AR stands for augmented reality. The package that we use, which is an open source package, is called AR track alva. And the markers are a 2D graphic code, which is quite similar to a QR code. So you can embed a ID or a string into the marker to differentiate between multiple markers. Usually first you have to create a marker, but for this talk we already have one created. But in any case, you can see the command down here to create your own marker. And 10 in this case is the ID that we give to it. And this command will create you a image which you can then print out and then you attach it to where you want to attach it. Okay. Now we have a little hands-on exercise for setting up the depth camera for the simulation. So, for example, we have parameters like the update frequency of the camera, the horizontal field of view, the resolution. But more importantly, we define the topics which are published by the plugin. For example, the camera info and the point cloud, which we need for tracking. So we can see that this configuration is in the MPO 700 Gazebo Sacro, which includes all the plugins which are loaded in the simulation. So for this exercise, we just copy this configuration and we open the IDE. It's better if you put it in a new tab so you have more space. Right. I guess we still have all the tabs open from last time. Let me close them. So this is what you would see. We go into the simulation workspace, source, new simulation, and then let me double check. Robots, MPO 700, ROS, robots, MPO 700, ROS, and then we have the MPO 700 Sacro here. as you can see, we already have some plugins here, for example, for the LiDARs. And here we add our configuration for the depth camera, like this. And we save it. All right. And next, we will set up the AR tracking package. There's some important parameters that we need to specify. For example, the marker size, which is 7 centimeters in this case. And of course, the topics, which are subscribed to, for example, the camera info and the point cloud, which of course should match what we specified in the Gazebo plugin. So for this exercise, we copy the configuration. And this time we go into simulation workspace, source Neodocking launch. So here I have simulation workspace, source Neodocking launch. And then we use the AR track alva single launch file, and single meaning that we only detect, we want to only detect one marker. And you can see here the node is started, and we will add our parameters down here. And save it. Okay, now we have set up the tracking package. And there's one last final step we have to do, which is for the simulation. By default, we do not start the autonomous navigation, so we have to enable it. The autonomous navigation includes MoveBase. It includes our own localization, which is called Neo localization. And in MoveBase, we have configured to use our Neo local planner. Okay, let's go to the simulation launch file and enable the autonomous navigation. So again, we go to the IDE. We are in source Neo simulation. And this time we go into launch. And here we have simulation launch. And here we have the parameter that we have to enable, set it to true. And save it. All right. And now we are pretty much ready to go to start the simulation. All right. For this, we go back to the ROS checked. And because we modified the parameters, we have to restart the simulation. And for that, we go to simulations. We choose launch file, which will be at the very bottom. You can see Neo simulation package and then the simulation launch file. And we launch that. Now we can see our MPO 700 being loaded slowly but surely. All right, let's increase the window a little bit. Okay. First, we will check the topics and make sure the simulation is all good. For that, we do ROS topic list, and we can see all our topics are available. Okay, next step would be to move closer to the docking station because the docking only works once the marker is visible in the image. So for that, we use move base. So we go back to the ROS checked, we go to tools, graphical tools, we start always, put in a new tab, and resize the open tab. All right. And here we can see the camera image. Let me increase that a little bit. Yes. And zoom out here a little bit. We can see where we are right now. We are in this little box here, and the docking station is somewhere down here. Let me show you in the simulation. Yes, down here. Here we can see the docking station back here. So we have to move over there. For that, we go into RVis, and we use the 2D navigation goal. And it's important to note in this case, for this setup, the docking attachment is in the back as well as the camera. So we need to be facing backwards to the docking station. So let's move somewhat close to the docking station, setting this navigation goal. Now you can see the robot is turning around because it always wants to move forward. This is how our local planner is configured. And we can see in the simulation, we are moving over there. Okay. Now we are almost ready for docking. Let's check again that we can see the marker. Yes, we can see it here in the middle. Okay. Now let's see what the next step is. We will launch the docking package for which we have created a launch file already, specifically for the simulation. So in the ROS check, we go into the terminal and we source the environment. So we go in simulation workspace and then we source the environment like this, and then we will start the new docking package using the launch file, which is ROS launch neo docking, and then the launch file doc with individual marker sim for simulation. Okay, we start that. Okay, and it's telling us it has 3 markers loaded, 2, 8, and 11, and 11 is which we will use today. Okay, now we should see that the marker is detected, and for that we go into RVis and zoom in a little bit. You can already see the coordinate frame, which is published on TF. Yeah, so we can see it's detected. We have the coordinate frame here. And which means we are ready for the docking process, which is started by using the auto docking service. So let's copy this command, ROS service call auto docking 11. And 11, of course, is the ID of the marker which we use today. So let's open another terminal. All right, we got that. First we have to go to the simulation workspace again and source the environment again, just like we did before. And now we can start the docking process by calling the service, which I do now. Yeah, seems like it worked, but there's some warnings. Okay, our robot is already docking in the process. That was first stage, this is second stage. And now comes the final stage. All right. Yes, we are docked. And we can see we moved a little bit too far, which is for a little exercise was on purpose. So we can show you how to adjust the parameter for the desired docking position. So since we have, I guess we have some time left, so we will adjust the parameter to match the correct docking position. And for that, we go back to the IDE. And we go to, again, simulation workspace, source, and then neo docking. And we go this time in configs. And then auto docking. And then we have a YAML file called stations. And here you can see the position that we want to dock at relative to the marker position. So right now it's saying we want to be 30 centimeters in front of the marker, which means the base link origin will be 30 centimeters before the marker. And we realized we moved a little bit too far. So now let's move a little bit back by adding 1.5 centimeters like this. So now we have 0.315 and we save it. And we have to restart the Neo docking package. So we go into the first terminal, we do Control C, and we start it again. Okay, now we're ready again. So first we have to reset the robot to a starting position again. So we go to AVIS and move back a little bit. Give it another 2D navigation goal to move back. And we can see the marker is detected again. Okay. Then we can go back to the ROS checked and start our second approach by, yeah, there's some warnings from PCL library. It's no big deal. We saw in Avis the markers detected, so we can call the auto docking service again, which I do now. And we are moving. First stage. Now I take the second measurement for the second stage. All right, and now a final stage. Yes, and we can see now this is approximately where we want to dock, in the middle of the range that we have. Yes. All right, this is much better than the first approach. And also we can try different starting positions to make it a little bit more difficult as an exercise. And let's go back to Avis and move to a slightly different starting position. Maybe a little bit off center, like this. All right, we can see marker is detected. And we go back to ROS checked. And we start the docking process again, calling auto docking, ID 11. Right. Let's see, first stage is reached. Now second stage. And final stage. Yes. And in the terminal, we also get some information output regarding the final docking position that was reached. The first one is not really, doesn't tell us much, but the second value is the arrow in Y direction, which is sideways to the docking station. We can see we have an error of 2.5 millimeters. And the third value is the angle error, which is 0.017 degrees. So it's quite accurate. Right. I hope you were able to follow the talk and manage to get the docking process working for you.
Thank you very much, Max.
Yeah.
Impressive demo. Thank you very much. And it's impressive these 3 times that you launch it at the end with different positions and different orientations and so on. So amazing, and all of them, and then also changing the parameters in directly and everything working again and again. So repeatable experiments. So very, very good, very good.
Yeah. Thank you for the great opportunity for presenting at your conference today.
Oh, it's our pleasure, of course. It's our pleasure. And then let's go for a few minutes of questions for you, if you don't mind. Sure. We are a little bit late because of the previous speaker delay, but there's no problem. So on our side, there is time for those questions. Is that okay for you?
Yeah. Well, let me show you our final conclusion.
Sorry. I thought I thought that was okay. Go ahead. Yeah. Sure.
Just real quick. Just the packages that we use today. It's actually 3 packages. So we have our Neo local planner, our Neo localization, and of course the Neo docking package. And down here we have the links to all the repositories. It's all open source, and you can use it for any robot. For example, our Neo local planner, it supports omnidirectional as well as differential, and it works for any robot that you want to use it. And our Neo localization is like a drop-in replacement for AMCL, which is more accurate for such docking procedures. So using the Neo localization, we can reach a couple of millimeters of accuracy. And yeah, of course, in the Neo local planner also, we created in such a way that it allows us to reach accuracies of a couple of millimeters. Yeah.
Well, final. Very cool.
Yeah.
Okay, so thank you then again, Max. Can we see you? Yeah, perfect, great. Thank you very much, Max. So now let's go to some of the questions, and then here we were discussing when we were watching your presentation about the fact. So we were discussing, but what is considered docking or not docking? So because you use the navigation system, the ROS navigation stack, for moving the robot from the cage that it was, this room, let's say this room, to the area where the docking station is visible to the robot, right? So can you explain the difference to the audience between the first navigation until the area and then the second one, which is actually the docking behavior, the per se? So it's not that the robot, what I mean is not that the robot that is looking around for the charger or something like that, right?
Yeah, no. So this would be part of your application is like, how do you reach the starting position for docking?
Yeah.
It really depends on your application. So this is outside of the Neo docking package. the difference would be, well, there's not much of a difference because we use MoveBase for both the initial approach, the initial position and the docking process. But of course, in the docking process, we use the feedback from the camera to calculate the target position or the goal position, right? And in the first case, you define it. It's most likely it will be statically defined. You have some configuration where you say, okay, here's the starting position for this docking station, right?
Yes.
So, and for the docking process, the position is automatically computed based on the marker. So when the marker is in the right position, then you can be sure that it's all good, right?
Exactly. So it has to be, the marker has to be in the view of the camera. So there is a kind of a radius to which the docking behavior is able to work, right?
Yeah, it's approximately 2.5 meters.
Wow. Okay, that's more than enough.
Of course, it depends on the camera that you use, but this 2.5 meters is, for example, for the Intel real sense that we use.
Okay.
Yeah.
Okay, so then please, sorry, I didn't mention to the audience, please put your questions on the chat so I can present to Max. And so far, what I'm seeing here are the comments that say how nice and great was the demonstration of the docking, you know, because it also impressed us a lot. And then in the meantime that people is putting their questions. So you mentioned that also this package can be used for other robots, and how much change for another robot it is? How much do we need to modify the Neodocking package for that?
Yeah, so I think most of the work would be adjusting the robot model, the URDF, to define where you mounted the camera, and
Okay.
also getting to work the camera driver for your camera.
But yeah, but that's a normal for any other software.
Yeah.
So nothing special then.
No, that's not much special. No.
Okay, and can you tell us why you did select the AR tags for indicating the location of the docking instead of using QR codes, for example, like you mentioned at the beginning, that are very similar?
Yeah, I would suppose the reason was that the availability of the AR track Alva package. So the CHAO decided that this would be the best way to get a good pose estimation of a marker.
Yeah, because it's already available in ROS also, and
Yes.
I think that the markers are bigger also, so
Yes, they are bigger. Yeah,
they can be. Yeah.
Yeah, you choose the size. You can choose a size.
Okay, great. So here there is a question from Serge Simard, who says that he would like to know better the definition of the 3 stages of the approach of the docking, because he doesn't see very clear what is the purpose of each one of those.
Right. So initially we only had one stage, and we quickly realized that it's not accurate enough, because when you use MoveBase, you send a goal and then it moves to the goal position, right? So, but in the initial position, you're quite far away from the docking station, so your pose estimation is not really good. It's maybe a couple centimeters of accuracy, which is not enough. And then we added the second stage to get. So in the second stage, we are closer to the marker, so we get a more accurate estimation of the pose. But also that we realized in extreme cases, if you like, the angle is really, you have a really steep angle to the marker, especially then the pose estimation is really difficult. And to also cover that extreme case, we added a third stage, which is like maybe 20 centimeters of distance to the docking. So where we get a really accurate final measurement of the marker pose, and then we send the final goal move base. Yeah, so the reason for the stages is really to get a more accurate docking, a more robust docking. And I guess you could also send the goals while you're still moving, but this is our first version of the package, and we wanted to keep it somewhat simple.
Okay, fair enough. Yes, and yeah. So I think that this is answering another question that is beneath. But before that, he says Daniel Martinez. Let me see. No, sorry, Pratik Nagra says, does the NeoLocal planner support differential drive robots?
Yeah, I mentioned earlier. Yes, it does support omnidirectional. It does support holonomic, and it does support differential. So there's a Boolean flag which you can set. I think it's differential mode or something, and you set it to true, and then it switches to differential mode. Yeah.
Okay.
And the differential mode also supports because differential planning is really difficult because in the end you cannot just make a correction in Y. So our NeoLocal planner also supports the case where in the end it detects, oh, I need to move in Y.
Yeah.
So then it rotates again and rotates back again. So yeah, it's really tricky, but it works.
Yes, that's something I also have experienced, especially when you are very, very close to the target. Yeah. It's very difficult with differential drives, yes. Yeah. And the question from Daniel Martinez is, why do you subscribe to the points for the AR track instead of to the image raw?
I didn't understand quite clearly.
Yeah, the question, so I think he means that you are subscribing to the point cloud when you are trying to detect, subscribing to the point cloud to detect the AR track instead of the image raw.
Yes. I would say the reason is because the AR track package is set up in this way. So it was developed to accept to work on point clouds, which you can see it's also using the PCL library, which is a point cloud library. That was, I guess it's just a choice that the developers made for the AR track Alva package. And so we give it the point cloud, yeah.
Okay.
But you're right, you could also do it using the image and using the RGB and the depth image. But yeah, they chose to do it using the point cloud.
Okay. Okay, so there are many other questions there. So they finally started to start. So but we have to finish here today. So if you want to answer those, you can go to the chat on the video and then answer them if you want. You feel like it would be great.
Yeah, Pradeep is right beside me.
Okay.
He's doing exactly that.
Okay, great, perfect. So Pradeep is from the team of Max, and he's also on the chat. I can see now. Okay. So he is answering the questions. So thank you very much, Max.
Yes.
Thank you for an awesome presentation. Bye-bye.
Bye-bye.
And now, Jen, what's next?
We already finished all the speech. Thank you so much for all the speakers. Yeah.
Yes, they're very good, and that was the last one. And now we are ready, about to go to the last section of the conference.
Yes, but before that, we are going to have a 15-minute coffee break, and then we will be back for the ROS Awards 2020 ceremony. And before that, we have an extra quiz, right?
Yes.
For our attendance.
Yeah, so actually we decided this quiz, it was not programmed, so we decided along the day, based on one comment that one person did on the
social media.
On the social media, and then I lost it with all of them. And then it was, I think he got it as, let me see, not there. Okay. Well, I wanted just to mention the person, so I'm going to check it out later. But basically, this person on the social media was mentioning that in most of the videos that we show you on the quizzes, they are showing the screen of a person who is using the tool that we are presenting, for example, the WebViz or the Habitat Simulator or any of the others that we have been showing. they were showing a user which is called RDaniel. Okay, so I'm writing down this here on the chat is RDaniel. Then this person spotted that this was an Easter egg in the videos, and could be. So what we decided is not to put any video here. So the question that is for the person that is going to win this last quiz is to identify, well, you have to identify who is this RDaniel, from where it comes, and basically the question is, what does it mean the R before Daniel? So the first person that has the question answered on the chat will win the last t-shirt sponsored by eProsima, and the last mug, ROS Developers mug, is sponsored by Robotics.
Yeah, exactly. So okay. Now let's have a coffee break.
Yes, coffee break
15 minutes.
And come back in 15 minutes.
Yeah, for the ROS Awards Ceremony. See you now.
Great. So we are here on the last section of the ROS Developers Day, and we are about to conclude with the last quiz solution and who is the winner. So actually the winner, the R corresponds to robot. Okay, so that's the correct answer. Then if we are fair, the winner is Bite Gritty because he said surely robot. So that's correct, okay? However, we are going to deliver a second set of t-shirt and ROS Mag. T-shirt is sponsored by eProsima and the Max is sponsored by Robotics. And we are going to deliver a second one because there was a very nice explanation of this R meaning and where it comes from Ali Khoshidi Benam. So he explained that R. Daniel Oliva is a fictional robot created by Isaac Asimov, and the R initial in his name stands for robot. That's a perfect explanation. So you deserve also to have this second set of t-shirts and mag. So congratulations.
Congratulations.
And then we set here, final, all the quizzes, all related to the ROS Developers Day speeches and so on. And I hope that you had a very, very intense and very inspiring also list of talks that will make you have a better future.
Yeah.
So what it takes now? What is the next point?
So now let's start the ROS Awards 2020 ceremony.
Okay.
So the intention of these awards is to express the recognition to the individuals and the company that contribute to the ROS and robotics community, and also for the development of ROS-based robot industry. So today we are going to announce the best ROS software and the best ROS robot and the best ROS product and also the best ROS developer.
Yes.
So we are going to send you a plaque for all the winners. And yeah, and this event, this campaign, we will start about 3 months ago, right?
Yeah, so the votes that have been collected by a website that we set up 3 months ago, and then all the ROS community had the chance to vote for the favorite ROS package, ROS robot, ROS product, and ROS developer. So we said that website, you vote, you ROS developers of the world, and then that's the results of this voting that we are going to present here today.
Okay, great. So the first award we are going to see is the best ROS software.
Software, okay. And for package. So let's go for the finalist of the best ROS software. And we have 4 finalists. Usually it should be 3, but in this case, the 2 ones on the last in this category. So they had the same number of votes. So we included a 4th one. And then they are, the first one is Plot Juggler. That we have been using this around this conference today. Then we have the Slam Toolbox, and then we have the Move It, which also we have used it along today in several of the speeches, and also we had Arbis that has been used in, I don't know, in 90% of the speeches also. And now let's go for the winner.
Okay, so thank you, my colleague. I already have the envelope for the best ROS software. Let's see who is the winner.
Okay, let's see.
Okay, so the best ROS software is Move It.
Yes! Bravo! Bravo, Move It! Bravo! That company, and especially to Dave Coleman, who is the leader of this program, of this package. He's the leader. Congratulations.
Congratulations. So the next award we are going to see is the best ROS-based robot.
Okay, then for the ROS-based robot, we have 3 finalists. The first one is Turtlebot by Willow Garage. So you know the Turtlebot you have been using. You know Willow Garage because you are ROS developers. Then we have the Husky by ClearPath. And then we have the RB Kairos by Robotics. That's another robot that we have been using today in the presentations. So now let's go for who is the winner.
Great. Here. Yeah.
Okay.
Let's see who is the winner.
Okay, let's see.
The best ROS-based robot is Tuttlebot by Wirral Garage.
Okay, great. It's very clear because it's been for all the ROS developers, that's been the first robot that we have. Most of us we have started in. Then Wirral Garage is defunct, so it doesn't exist anymore. Then, but the stick of Wirral Garage has been taken by the Open Robotics. So we are going to send this plaque to Open Robotics. Because actually, some of the developers of Tuttlebot, they are still there, which is To Live Food. And then there is Melanie Wise also, who is in another company, but okay, so that's it.
Great. So now let's see the next award.
Okay,
The
which
best ROS product.
one? Okay, so for the ROS product, it means a product that is running ROS in the inside. So usually it should be a solution that includes robots. It's not necessarily like that, but it's a product that is sold. Okay, so then we have for the finalists, and then for the finalists in this case we also have 4 finalists. The first one is Locus Warehouse System by Locus Robotics. Then we have Leo Robot by F&P Robotics. Then also we have the Fetch Air System by Fetch Robotics. And then we have the Toru by Magazino. So let's see who is the winner.
Thank you. Okay, let's see who is the best ROS product. It's Toro by Magazino.
We'll send the plate to Magazino company. Great.
Congratulations.
Congratulations.
So now we are going to announce the last award, very important, and it's the best ROS developer, the person behind the robot, behind ROS, all the product.
The person.
So, yeah, the person.
Exactly.
So let's see, who are the finalists?
Yeah, so we have 3 finalists here. One is Davide Faconti, who actually is is a developer of the SLAM toolbox and also is behind the behavior trees packages that you have seen on one of the presentations. Then there is Steven Masensky, who is the developer of the SLAM toolbox, which is also mentioned was a finalist in the best ROS software category. And then he is also the developer, so he has published recently the navigation tool system and a paper about that, so amazing. And then finally we have William Rudell, who is a ROS developer at Open Robotics and is one of the persons who has contributed most to the development of the core of ROS. So who is the winner for the best ROS developer 2020?
Okay, we already have the last and variable leg.
Yes.
So let's announce it together.
Okay.
1, 2, 3.
Steven Masensky. Also to all the nominees, only one can win, and that's the result. We are going to publish anyway a report next week with all the information that we have received by doing this votation. So you are going to see all the statistics, which are other possible finalists that could be but never reach the top 3, and some other interesting information that we have deducted based on those data.
Yeah.
And that's the end.
We're almost close the 3rd ROS Developers Day Online Conference, right?
Yes, and I would like to close this here today. It's been a long day, and I hope that it was very fruitful for all of you, so that was paying the price for being here. Then I would like to conclude with a quote that I like very much. It says, "We can see the past, but not influence it. We cannot see we can influence the future, but we cannot see it. Okay, so what I would like to apply is this sentence to use what we have learned here as the past to influence our future.
Yeah. So dear ROS developers, thank you so much to stay with us until this last moment. And we hope you learned a lot and also be inspired by our speakers.
Yes.
So I want to say, I hope to see you in the 4th ROS Developers Day Online Conference in 2021. And don't forget to keep pushing your ROS learning. Bye.
Bye-bye.
Dos, tres.
I can't believe it. It's impossible. Let me out! Let me out!
you.